I guess we can start now. Dear participants, dear colleagues, welcome to last day of our summer school, Uyghur 2021. It's my great pleasure to introduce you our lecturer, Ronny Hänsch from German Aerospace Center, DLR. In this lecture, he will be talking about SAR, deep learning for SAR processing and analysis. Ronny, stage is yours.
All right, thank you. Let me just quickly share my screen. All right, so I hope you can hear me all right and my screen is visible.
Yes,
yeah.
Perfect, thank you. Well, yeah, thanks for the introduction and thanks for having me. I'm very delighted to give this talk about SAR. Just for the participants, so if you want to have the slides, you find them under this URL. Just go there and download it from Dropbox. All right, so quickly about me. I spent most of my early career in Berlin, in Germany, at the TU, did there my PhD and then stayed a little bit as a postdoc at the computer vision and remote sensing department. And then 2 years ago, nearly 2 years ago, I joined the German Aerospace Center, in particular the Microwaves and Radar Institute that is close to Munich in Germany. But I keep my connection to the TU Berlin. I still do teaching there. Well, in the last year, of course, that was virtual, right? But otherwise, I would also just go there. I give a lecture on digital image processing. I organize some seminars and projects and things like this. Also, I continue to do supervision for master or bachelor projects. Well, this is actually also my second time I do teaching in Turkey. Unfortunately, again, only virtual. A couple of years ago, I was part of the flying faculty for the Turkish-German University in Istanbul. So I had some experience visiting this very nice country and enjoyed this very much. Regarding for community service, I was co-chair of the IEEE GRSS Technical Committee on Image Analysis and Data Fusion. And now I'm the newly elected chair for the next 2 years. So again, some responsibility, but also a job I'm looking very much forward to. I'm also the editor-in-chief for the GRSS newsletter, the e-newsletter. I'm an associate editor for the Geoscience Remote Sensing Letters and guest editor for JSTARS. And of course, I review for all of the GRSS journals and for most of the major computer vision conferences. So if you don't know what is IDF, the Image Analysis and Data Fusion Committee, just in order to put this a little bit in perspective, most of those people you already know because they have given the lectures in the summer school in the last days. And by chance, this is not by design, but by chance, nearly half of them are affiliated with IDF. So there is me, which is the current chair. Then there is Claudio, who is the current co-chair. So helping me fulfilling the responsibilities of IDF. There's Venci, which is the current leader of a working group within IDF. And Davis, who gave his talk yesterday, is a former chair of IDF. So you see, we are very active and trying to reach out and provide the community with talks and organizing different things. So if you're interested in what is IDF doing or GRS in general, please reach out. You can also join the technical committee, which would mean you receive our monthly newsletter. You can follow us on Twitter and so on. Research-wise, well, I'm focusing on machine learning, deep learning, mostly random forests. Random forests, this is one of the decision trees I'm usually working with, a visualization of that. But not just in general, but I apply this, of course, to image data, and mostly this is parametric synthetic aperture radar data. And I guess this is why the organizers of the summer school asked me to give this talk about how deep learning is used for SAR. I also do a little bit of image processing and, of course, computer vision. About the DLR, so the DLR is scientific institute in Germany. It's basically the space agency of Germany, and it has a lot of different institutes distributed over whole of Germany. My institute is down here in the south, close to Munich. So Munich is basically here. My institute is in a very small town with a very complicated name, which is called Oberpfaffenhofen. So this is how the campus looks like. So basically this part here, this is the campus of the DLR. Here you see a runway of an airport. There's a small town, a highway is going on here. So this is a railway track. So this is of course an optical image, but since my talk is about SAR, this is how the same scene looks in a pulsar image. So you see we also have colors, although it's not really color what we're seeing here. I will cover this later. So again, this part here would be the campus. And if you zoom in a little bit, if I'm not mistaken, my office should be here. So you can already see, well, when we have a nice SAR image, and this image is nearly 30 years old, we can still interpret it as humans with some experience, right? Some things are more difficult than for optical images. So you need some expertise to really interpret it. But nowadays, when we show modern SAR data to laymen, well, I would say like 80% of the images they can still understand. But yeah, hopefully after the talk today, you will understand more than that. So what my institute is doing, we make a lot of research on active systems, like for example, SAR, also some passive microwave systems, but always microwave. So there's not much optical sensors that we are using. My department is mainly focusing on FSAR. So this one here is the ESAR sensor that was also built by the DLR, but now the new sensor is called FSAR. So it's an airborne system. This is the plane we have where the sensor is mounted. It's a multi-frequency polarimetric SAR sensor, and it gives really, really nice images. I have some examples later on. All right, so much about me. Now, what can you expect in the next 2 times 90 minutes? I want to start with a brief introduction to SAR, because I expect that not so much of you really know the details about it. Of course, I can't really go into all the technical details of SAR, because then I would need more than the 2 times 90 minutes to cover everything. But at least I want to make the most important concepts I want to make clear, because otherwise you won't understand the topics we are covering later on, right? So if you don't know what is layover or the speckle, you won't understand the deep neural network that is trying to reduce speckle, right? So I will cover a couple of basics for SAR in the next few minutes. And then this big bunch here of topics is all deep learning, right? So how can we use deep learning for spectral reduction? How can we use deep learning for parameter estimation, and so on? So my goal is that what you take home from the next 2 times 90 minutes is a general understanding of basic SAR concepts and a lot of examples how deep learning is used in the different stages of SAR processing. We start with image processing, like noise reduction, and then at the end we do some semantic analysis of SAR images. If you have questions, please put them into the question and answer box, either here on Zoom or on YouTube. I will make breaks during the talk, and then the organizers will help me to go through at least the most important questions. All right, then let's get into it. So let's start with an optical system. Somehow the Zoom box is not going away. Okay, never mind. I hope it's not blocking anything for you. So an optical system is usually a passive system, right? So this means we have our sensor, but the sensor relies on a different source of energy, either energy coming from the sun reflecting at the surface, or energy that is directly transmitted from the surface of the Earth, right? For example, that could be thermal radiation. The most well-known, well-understood optical or passive systems are optical systems. For example, digital cameras, they're so well-known and well-developed that everybody has one of them, right? So you probably have your mobile right with you, right? All mobile phones, or nearly all of them, have a digital camera, and they can be described very well by a so-called pinhole camera model. Here you see a schematic sketch of that. Of course, it's not really a pinhole camera, because you have lenses, but still this model is quite accurate to formalize what is going on in the image formation process. So you will have the projection center of the camera, you have a 3D point, and this 3D point is projected onto the retinal plane of your camera. So this would be the image formation, can be either in front of the projection center or can also be behind. Mathematically, that is the same. The important thing here is that the position to where the 3D point is projected depends on the angle, right, between the 3D point or this vector that is connecting the 3D point with the projection center and this so-called principal axis here, right, so the depth direction. So where the projection of this 3D point ends up depends on the angle. Well, and then what is happening during the image formation process is that once the slide is hitting our retinal plane, we have a couple of light-sensitive sensor elements. They are counting the photons, basically. Usually they are light insensitive, so they are not sensitive to any kind of frequency. In order to have a color image, you put in front an array of color filters. Usually green is dominant because humans are very sensitive to green, right? So you have more filter elements that are only letting the green light through. And then very often, at least in the digital cameras that we use, you have a filter for infrared light as well. So this is how you form a color image with a digital camera. There are other frameworks as well, right? But this is, well, how most common digital cameras work. How does it look like? I mean, you can't just have it in your phone. The cameras that we are using in remote sensing look a little bit bigger. You can mount them on planes or on satellites, and then we can acquire images of the Earth in a really high resolution. So this is an example from the Data Fusions contest from 2018 that was organized by ADF. And here we had, among other sensors, a 5 centimeter resolution optical image. So really high resolution acquired by a plane. But of course, we not only have RGB images, we can also have hyperspectral imagery that you already had heard about in some talks in the last days, right? Which is also an optical image, but the number of spectral bands you have is much, much higher. So in this example here, we had 48 different spectral bands, so it's more multispectral sensor in a certain range. And of course, since we want to increase the radiometric resolution, we have to decrease the spatial resolution a little bit. So this is not really high resolution anymore. It's 1 meter, but still not that bad. Well, those are passive systems, right? Again, they rely on an energy source that is not their own, usually the sun, right? When we talk about optical systems. On the other hand, we have active systems. So active systems are systems that come with their own energy source, right? That can be laser, right? So laser scanner, LiDAR, so also optical systems, but of course also radar, right? So radar is using microwaves, so electromagnetic waves in a different frequency spectrum. But the idea is the same. You have a sensor that is emitting a signal, right, either optical or microwaves or whatever, and then measuring the echo in one way or another. So, as I said, it can also be optical, for example, LiDAR, right? So here again, an example from the Data Fusion contest, where on the same plane, we also had mounted a LiDAR sensor that was acquiring a 3D model of the scene in 3 different frequencies with a 50 centimeter resolution. But of course, I mean, this talk is not about optical systems, right? This you already have heard in the last days. This is about radar, right? So optical systems live somewhere here, right, in the frequency spectrum. We will talk about systems that are using this part of the frequency spectrum. Right? So much higher, well, much longer wavelengths. All right. So why does it make sense, or why is this interesting? What you see here in this plot is the absorption of the atmosphere of the Earth for different wavelengths. Right? So you see here is the optical part, right? And you can see for the optical light, our atmosphere is mostly transparent, not completely, but mostly transparent, which is really good because otherwise we would not have light, right? At least not in this frequency spectrum. And then here there's a lot of the energy is blocked by the atmosphere, but then here we have the radio waves, microwaves, and you can see here that they are just go through the atmosphere. So this means that, well, on the one hand we can have telescopes that are, mounted on the Earth and are observing space, and the radio waves are not blocked by the atmosphere. On the other hand, this means we can have satellites that are using microwaves and are observing the Earth without being blocked by anything, right? So atmospheric corrections are, well, you need to do this a little bit, but not much, but also clouds, for example, fog, smoke, dust, none of this plays really a big role when we talk about SAR. So we can look right through all these things. All right, so how does SAR work? So SAR stands for synthetic aperture radar, right? So let's start with radar first, and radar stands for radio detection and ranging. So the idea is you send out a short pulse of a microwave. This is reflected, or more accurately, backscattered on the ground in all possible directions, depending on what kind of medium you have. But among other things, it's also backscattered towards the sensor, right? So we can have one sensor that is emitting the pulse and then measuring the echo. In some systems, we can also have one sensor that is emitting the pulse and a different sensor that is measuring the reflection, right, or part of the backscattering that goes in that direction. But for SAR, in this talk, we will mostly talk about systems where emission and receiving is happening at the same place. And then we combine those echoes in order to have an image. What are the advantages? Well, a couple of them I already told you. We don't need to care about daylight anymore. We have an active sensor, right? We don't need to wait for the sun. So this means we can also acquire images during the night. It does not matter to us at all. Also, we are quite robust towards weather, because if there are clouds, microwaves go through them, right? So it does not really matter. And this means that, there are certain areas on the Earth where basically you always have cloud cover. So optical sensors there are close to useless. Right? With a radar sensor, you don't mind, right? You can always acquire images. Also, the information that we are acquiring is somehow complementary to the optical information. So we will cover this a little bit later on, but very often people now start to use radar images, SAR images, together with optical images. So the point I want to make here is not that radar or SAR is supposed to replace an optical sensor, but rather to complement it. The disadvantage is it's a little bit more complex. It's a little bit more complicated. The image formation is more complicated. It needs a lot of processing. And also the interpretation of what a SAR image really shows is a little bit harder to understand than for an optical image. Mostly because humans are not really trained to interpret that. And we are trained for optical image because our sensors, our eyes are optical sensors. All right, but well, with modern SAR sensors, you can have very nice and high resolution images as well as this one here. And even if you have never seen a SAR image before, I think you get the general gist of what this scene is showing, right? So you have some dense urban area here with high-rise buildings. You see some water area here, some bridge, and so on, right? The details might be a little bit complicated, but the general gist, even if this is your first SAR image you have ever seen, I think you understand. So what radar is basically doing is sending out a pulse and measuring the time it needs to receive the echo. Right? And one of the most straightforward things to use this is Itometry. So this means you will have a sensor in space. It sends out your pulse just downwards, and it's just measuring the time that it needs to receive the echo. Since the height, the distance of, well, the orbit information basically of the satellite is known, the time directly corresponds to the distance to the surface. And by doing this, you can measure the height of the surface of the Earth very, very accurately, right? So you can do this over oceans, right, to measure the height of waves, for example. Also, by using a little bit more complicated techniques, you can measure the speed of wind and things like this. Of course, you need to know the satellite position very, very well, right? Because otherwise you can't infer the height. You need to take the atmosphere a little bit into account as well. And of course, I mean, you have noise and drifts in the sensor, whether the sensor is in the sunlight, then it's heating up and stuff like this. But if you solve those challenges, you can have very accurate height measurements. So here you see an example of altimetry that was used to measure the height of waves, and in this case it was a tsunami, and you can nicely see how the tsunami wave is spreading over the area over time. All right. So this was there we go. Okay, so this was how to measure height, but we want to acquire images, right? And for acquiring images, we can't look just straight down anymore. So we can't have a sensor that looks like this, because if we have a sensor that looks like this, we can't distinguish anymore between a point here on the left-hand side and the point here on the right-hand side. So this is why for images, we need to have a side-looking radar. So this means, again, our sensor is mounted on a plane, but now we are not looking downwards, but we are sending the microwave pulse in this direction, right? Side-looking. So we can basically acquire an image of this area here. The problem here is that, well, you want to have images of a high resolution. And if you want to have a high resolution, you would need to have a very, very big antenna, right? Well, and a very big antenna is basically not possible on a satellite, and even on an airplane, it's well, you have your limits, right? The image acquisition itself, so the image formation process, is rather simple, but you can't get a high resolution, right? So usually it's something between 10 to 50 meters, and it only makes sense on planes. So you can't have this with a side-looking radar with a real aperture. You can't have on a satellite. It's too far away, and the antenna can't be big enough. You can do this on a plane, but even there, your resolution is very limited. But you can acquire images. So here you see an example of a side-looking radar image with a real aperture over Puerto Rico, right? So you can have a general impression of the general topography, right? So it is possible. But if we want to increase the resolution of our image, the only chance we have is to increase the antenna that we are using. But we can't put a big antenna on our airplane. So here is the idea of synthetic aperture. Synthetic aperture means that we are using a synthetic antenna by exploiting the movement of our sensor through space, right? So our sensor, in this case, again, an airplane, is sending out a microwave pulse and is measuring the echo. And then it moves a little bit further and it's sending another pulse out, right? It moves a little bit further, sending another pulse out. So it's recording all of these echoes along this flight path. And here, the next step is then to combining all of those echoes into a single image. The idea is that if we send out a pulse that is, coming from an antenna with a limited length, then you're illuminating a certain area on the ground. So it's not just the line that you're illuminating, you have a certain width of this beam. And this means that you're seeing the objects entering this beam and also leaving it again, right? So each object is seen for a certain amount of time in the different pulses. And then all of those echoes, they can be combined to a single image. And this is the complicated processing I was mentioning before. So this focusing, so this image processing, what we need to do is that the echoes that we are measuring from the objects, they might look like this in the raw data. Now, the first thing what we need to do is a so-called range compression. So we need to distinguish whether an echo is coming from this part of our illuminated area on the ground or from this part. So this would be the near range part. This would be the far range part. So this is called range compression. And then the other part is azimuth compression. This is then combining all of those different echoes that are acquired by different positions of the sensors into a single pixel. So how does it look for a real SAR image? So this is the data that a SAR sensor would acquire. And as you can see nothing, right? It looks like noise, right? There are no structures visible at all. Now, if you do the range focusing, then it looks like this. So already here, I mean, it still looks like noise, but you already see some structures, right? You see this hyperbolas here, also down here. And now the last step is doing the azimuth focusing. Right now we are compressing everything in that direction. And then we have finally our SAR image. So this was very much simplified. There are a lot of things going on because, for example, the plane is not moving very straight, right? So even if the pilot is doing his best, it's still with wind and so on, it's moving a little bit around. And you need to compensate for that. So this is still, I would say, an active line of research, although the techniques are already very sophisticated, so they can produce very nice and very accurate SAR images, but still it's not a completely solved issue. There are still improvements on the focusing. But the important thing is we are able to produce those images. So how is the SAR image structured? So well, it's a 2D array, right? It's an image. But in every pixel, we have a complex value because what the sensor is acquiring is not just the intensity of the echo, but also the phase of the sent out microwave. And then we have something that we call fast time and slow time. So the fast range is the fast time is in this direction. This is a so-called range direction. So the direction in which the SAR sensor is looking. So the flight direction would be in this way. So the airplane is going this way. This is the direction in which the microwave pulse is sent out. So this is called range. And the other direction in which the airplane is moving is called azimuth. So this is important to understand SAR images, right? A SAR image always have an orientation, an intrinsic orientation, different to an optical image, right? The optical image I can turn as I want. This is not possible for a SAR image. So for a SAR image, there's always an azimuth direction and always a range direction. And the things you will see in a SAR image behave very, very differently in those directions. So if you show me a SAR image, I can tell you in which direction the sensor was looking, right? This is not really true for an optical image. So in contrast, if you remember when I was briefly talking about optical images, I said the position of an object where it's projected into your image, it depends on the angle between the looking direction of the sensor and the direction of the object. For SAR, it depends on the distance, right? So what SAR is doing is really more like a time measurement. It's not depending on the angle. Well, SAR is already quite old, right? So the first Spaceborne SAR is from the mid-60s. Of course, here the resolution was not so good, right? It was 2.3 meters in azimuth. That is all right. Because you have this really long antenna, right? So the synthetic aperture, but it was only 25 meters in slant range. And of course, from there, we improved a lot, right? So now we not only have SAR sensors that are measuring things in only one channel, we have multi-channel SAR images using, for example, different frequencies, different polarizations. I will talk about this a little bit later as well. So those can be used for producing this kind of color visualization of a SAR image, and also the resolution is improving a lot. So nowadays we have a lot of different Spaceborne SAR sensors. Here you see some of them. One slide was not enough, so here you see a couple more current ones. But even those, they are not. So this list is not complete, right? There are many nowadays also commercial satellites, for example, from Capella Space, from ICE, that are acquiring high resolution SAR image from every point on the Earth. And if you combine all of those sensors together, basically every few days or some parts of the Earth, even multiple times per day. So to show you some examples how a modern SAR image looks like. So this is an image from a German SAR sensor, TerraSAR X. It's already quite old, but made a lot of good data acquisitions. So you see a very nice delta of a river, right? This part here is mangrove forests. This is an image of a volcano. If you see this circle around here, well, this is not an issue of the data acquisition. The circle is really there. You also see it in optical images. The reason is that this is a national park around the volcano. So there people are not allowed to cut the forest down. And outside of the national park, they cut the forest down for agricultural fields. Here you have an example of an airport comparing two different image acquisition modes. One with something that is called spotlight. So you see here the shadows of airplanes. And if you have a staring spotlight where the satellites look a little bit in front, and then while it's moving, just goes back and looks then at the end also back. So you have a longer time where you see the objects. So you have basically more information to combine. So the resolution is increased, and you can see that the image quality is getting much higher, right? Resolution is getting better, but also this noise-like phenomenon, it's called speckle, we'll talk about this in a minute, is also getting much better. This is also a volcano over Iceland. The color what you see here is coming from different dates, right? To show changes, how the volcano changed during an eruption. Yeah, so for spaceborne sensors, well, there are a lot, and we can produce very nice imagery with a lot of information. But of course, we also have a lot of airborne sensors. Again, here you see some examples. This is an example from my department. So just in case, if you're wondering how a SAR sensor looks like, this is how it looks like. So this is the interior part of this airplane. And all of this racks here, they are concerned with producing the microwave, sending it out, and then recording the echo. And you can imagine, I mean, this needs to be done very fast, very accurate. You have a high sampling rate. You need to record a lot of data very quickly. So there is really a big challenge on the hardware. So this sensor, it's quite amazing for me. It's obtaining SAR images in different frequencies at the same time. It's doing a fully polarimetric acquisition. So you get those nice color images, and you can even do interferometry with it. So it's really nice. And those is how those images could look like. So you see here, it's a really high resolution. You can see roads, those fluffy clouds here that are individual trees. You can see here agricultural fields. You can see power lines that are going through the data. You can see the different states of the agricultural fields. Yeah, so you can even see tracks of the agricultural trucks that are, like, for example, harvesting the crop, what was planted there, and so on. And again, I mean, if this would be your first SAR image, probably you could understand the scene, right? It's not really looking like an optical image because it is something very different, but still you could imagine that this is a house, right? Here you see some trees, you see the small roads, even the dirt paths through the agricultural fields and so on. So now nowadays we're really able to produce highly informative images via SAR from the surface of the Earth. I was already mentioning that SAR is using different frequencies. You might ask why. And the reason is that different frequencies react very different with things on the ground. So the interaction of microwaves in different frequencies is very different. So for example, you might have X-band that is mostly reflected. So if I would have a forest like this, the reflection I would get is mostly from the top part of the canopy. On the other hand, if I have P-band, I get reflections even from the ground. So part of this is going through the ground. Part of it might be reflected on the tree trunk and then being reflected on the ground and then going back. I might have interactions in the canopies and so on. So for the different frequencies, I can observe very different parts of the objects on the ground, right? Sometimes it's just the surface, but sometimes I can even penetrate into the vegetation cover, into snow, into sand. So I saw before there was a question on the chat that was asking whether I can also penetrate snow and ice. Yes, that is possible, as long as it's dry. So the big problem for SAR is moisture, right? So if something is wet, then that is basically being reflecting the microwave. So if you have dry snow, dry ice, dry sand, you can, with radar, you can look through, right? Depending a little bit on the type of radar, but sometimes quite some meters actually. And I have some examples later on. So how is the microwave interacting with the ground? Well, this depends a lot on the roughness of the ground. So if I have a very smooth surface, for example, a water surface that is not disturbed by waves, right? or sometimes also roads, or the runways of an airport, then I might have only a reflection, right? So the SAR signal goes in, it's reflected away from the sensor, so I don't receive any echo, and this part of the image will be black. Now, if the roughness is increasing, more and more parts are just like scattered around, right? And some of this will be scattered back to the sensor, and this is the echo I'm receiving. And of this echo, I'm recording the intensity and the phase. So I can have this diffuse reflection, right? So on a rough surface, part of it will be reflected away, part of it will be reflected back to the sensors. This is what I'm measuring. I can have a mirror reflection on a very smooth surface. I can have something that is called a double bounce. So for example, the wave is reflected on the ground, it's reflected on a tree trunk or a building, and then reflected back to the sensor, right? So I have those two bounces. That's why it's called double bounce. And I can have the volume scattering, where the microwave is entering some kind of volume. For example, that can be vegetation, like a forest, but it can also be like a dense urban area. Inside of this volume, it's just reflected a lot of times, so not just double bounce, but a lot of times. And then part of it, at least, is reflected back to the sensor. So this is called volume scattering. And the nice thing is all of those different scattering processes change the properties of my microwave that I record. The intensity, the phase, but also the polarization and so on. And all of this I can measure and then use in order to, for example, do a classification. One point of backscattering I have not mentioned right now is the so-called point scatterer. This means that when in one resolution cell, you have only like one dominant target that is producing the echo. Right? And the most, well, the best point scatterer you can have is something like this, right? So this is really just like a pyramid that is more or less standing on the top, right? So this part here is open. So the microwave goes in and is basically nearly to 100% sent back to the sensor. Of course, not really to 100%, but really a big part of that. And the backscattering profile of this kind of like reflectors is very well understood. They are used for calibration. So all of those crosses you see here in the image are this kind of reflectors that we planted there. So this is again the campus of the DLR you have seen before, and we use them for calibration of our FSAR sensor. All right, so far about how is the SAR working. Now let's talk about some of the properties of SAR that make it difficult for humans, but also for machine learning methods or computer vision methods to understand SAR. And one of those things that is most dominant is speckle. So speckle is very often it's called noise, but it's not really noise in the sense that it's a random fluctuation. It's rather chaotic. So let me explain what I mean with this. So let's assume that this is a part of our ground that we are illuminating with a SAR sensor. Right? And let's say one of those grid cells here is 1 pixel in our image. Now, in one of those cells, you will have multiple things that are producing an echo, right? Unless there's like this kind of reflector there, right? You will have maybe multiple rocks or multiple pieces of vegetation. Each of them is producing an echo, and all of those echoes are interfering with each other. Right? So basically, this means when I record all the echoes that have been reflected in this resolution cell, what is happening that I'm adding all of their vectors. Right? I'm recording basically the interference pattern of all of those echoes. So this means that the amplitude that I'm measuring is not constant, right? Even if the statistical distribution of all of those things is constant in this spatial area, for example, it's the same agricultural field, right? So things don't change much, right? It's the same vegetation cover, but still, since the position of the individual plants, the distance to the sensor and so on is different, I will have those random fluctuations. And this is causing a certain distribution of my intensity, right? So sometimes it will be very bright, right? If I add this up by chance, it's ending up here. So I have a very bright part. And sometimes if I add up different random vectors, then my resulting amplitude or intensity will be quite small and I have a dark patch. So observable in a radar image is that we have this grain-like fluctuation of intensity that we observe. It's not really noise because it's not random. This means if you would be able to take a second SAR image at exactly the same position of exactly the same scene, this noise pattern would be exactly the same as well, right? Of course, it's not really possible. You won't get the SAR sensor at exactly the same position. Also, the scene will change, right? There's a wind, and then the vegetation is changing a little bit. But if you could, theoretically, the speckle pattern would be exactly the same. Right? So this is why I usually don't refer to it as noise, but more like an chaotic part of the signal. But very often it is modeled as noise and sometimes even called noise. So don't get confused by that. Well, but for a radar image, we not only have the intensity, we also have the phase, right? And if you look at the phase of a single SAR image, it looks completely random, right? It's a completely chaotic signal. So this would be the phase. So the orientation of those resulting vectors, right? The intensity is the length of the vector, and the phase would be the angle, the orientation of the vector. But as we will see later, for a single SAR image, the phase is kind of random, chaotic. But if you have multiple images, multiple SAR images of the same scene, there's actually a lot of information inside of the phase that we can harvest. Another rather weird effect in SAR images is called foreshortening. Remember that SAR is measuring the distance to the objects on the ground, right? And the thing is that when we have an evaluated object, for example, the top of a mountain, we are decreasing the distance to the sensor, right? So if I have those two parts of the mountain here that have roughly the same size, right, from A to B and from B to C, the length on the ground might be roughly the same. In the SAR image, this first part here is shortened, right? And this part here is a little bit increased, right? Depending on how high this top is. And you see this very strongly in SAR images, right? So here, the azimuth direction is in this direction, slant range is in this direction, right? So the sensor was flying in this direction, looking in that way. And you see here the foreshortening, right? So here you see that this is the mountain area. So this part was closer to the sensor than other parts on the ground. So this is shortened in our SAR image. And if you want to correct with this, we need to have, for example, a digital elevation model, so that we can correct for this kind of topography, and then we can have a SAR image that looks like this. Now, if our objects are even higher, right, even more steep, then foreshortening becomes layover. So layover means that you can't distinguish anymore between an object that is basically on this part of the wavefront, right? So all of the points on this line here have the same distance to the sensor. And since SAR is doing a distance measurement, right? So things with a certain distance end up at a certain pixel position in our SAR image, all of those points will be fused in a single pixel. So in our SAR image, the top of this tower here will be together with this part of the tree and with this part of the ground. Right, so again, you see this here. So it's again a mountain area with some river, right? Slant range is again in this direction. And you see here the top of the mountains, right? It's laying over into the riverbed, right? So part of this part of the river and the top of the mountain that is here has the same distance to the sensor, so they fall into the same pixel. So it's not just foreshortening over anymore, it's even more, so that it's falling towards the sensor. And this is why I said before, if you show me a SAR image, I can tell you where the sensor was flying, where it was looking. Because you always see, if you have elevated objects, you always see this layover, and then you know tall objects always falling towards the sensor, so you know exactly where the sensor was. And of course, you also have this with not just mountains, but also high-rise buildings, right? So if you have a SAR image like this, you might think immediately that you have like an optical scene like this, right? It looks a little bit like this, right? So you would assume maybe that you see this part here of the building, right? So that this part here that you see here in my SAR image, that you see that it's this part of the building that is closer to us. But remember, right, high-rise objects always fall towards the sensor, right? So the sensor is up here, right, looking in that direction. So this means that what the sensor is actually seeing is the other side of the building that is blocked for us in the optical image when we look from this direction below. Right? So it's not the part of the building that is closer to us that we see in the SAR image. It's a part of the building that is far away from us, right, on the other side of the building. So this is why it's a little bit confusing to interpret SAR images. And then, of course, if the objects are high, then we not just have this foreshortening and layover, they are also blocking part of the signal behind them. Right? And this is called shadow. It's another effect that we have. Again, for high-rise objects like mountains, right? So you have here, there's a foreshortening and layover, and here you have the shadow, where part of the signal was blocked by the sensor, by the object. And again, this tells you the orientation of the image, because shadow is always on, on the other side of the object as seen by the sensor, because we are the ones who are illuminating it. And again, you have this for all kind of objects, right? So here you see, this is the SAR signature of the plane, right? This part here that is a little bit brighter. And this dark part here is just a shadow that we see. So here you see a plane. This is a helicopter, a couple of cars or tanks or something like this. All right, nearly through with SAR. I hope you are still bearing with me. This is one of the last effects, and this is really weird. This is really freaking people out when they don't know what SAR is doing. So this was one of the first scenes acquired by TerraSAR-X. If you zoom in, so this small rectangle here is this part. So you see here railway tracks. And this part here, this line here is a train. Of course, this train is on the railway tracks, right? The train is not here, going through the river and so on. But it's displaced because objects that are moving in a certain orientation of the SAR image are displaced because, the way how the SAR image is processed, it's taking the Doppler effect of the waves into account, right? So to distinguish a little bit more the objects in azimuth direction. And if you have moving objects, they also have a Doppler effect on their own, and this can't be corrected. Right? So they're displaced, and this displacement is actually proportional to their speed. So you could actually measure the speed of this train based on this offset. Right? But yeah, if you don't know about SAR processing, I mean, this is really scaring people that moving objects can be displaced. You have this for trains, but also for cars, as long as they are moving in a certain direction to the center. I was talking about penetration and how we can penetrate clouds. So this is certainly true, but you can still see a little bit the cloud shadow, right? Because cloud is moisture in the air, and for certain frequencies, they are more sensitive to this. So you can actually have part of the signal being blocked by the rain cloud. If you have heavy rain, maybe not by the cloud, but at least by the rain itself, and then you might have this cloud shadow in your SAR images. So if people tell you that SAR is independent of weather, it's not really true. It's quite robust to weather because you can look through the clouds, but you can still have effects of weather inside of your radar images. Another example for penetration is penetrating with vegetation cover. So this became quite famous a while ago because with SAR you could see the ruins of old building structures in the rainforest that are covered by vegetation, so you don't see much of it in optical images, but with SAR you can penetrate, and then you see this old building structures. And another example was to see old structures in the desert, right? We were talking before that SAR can also penetrate sand to some degree. So this would be an optical image of a desert. And the interesting part was this track that you barely see in the optical image. But if I show you the radar image, you have this very nice color variation around this track. Right? So again, this is the optical one, everything is yellow because it's just desert. And this is this corresponding polarimetric SAR image where you can see a lot of different structures, in particular those old tracks, ancient tracks that people had formed. Now, a couple of things how we want to use SAR, right? One thing we can do is if we have multiple SAR images, in this case 2, we can use the phase information in order to create very accurate elevation models. So here the idea is that you have two SAR images, you can combine those two into something that is called an interferogram that looks like this, right? Nicely colorful. Then you need to do a couple of processing steps, but at the end you can have a very nice digital elevation model from that is highly accurate. So I showed you images of Terrace X before. A couple of years later, we launched an identical sensor. Then this two satellite constellation is called Tandem X, and Tandem X was recording a global digital elevation model, right? So now we have an elevation model of the whole Earth based on Tandem data. So how does it look like? So here you see the intensity information of the SAR image over some volcanoes in Ecuador. We can combine two SAR images in order to get the interferograms, and then based on that, we can have a very nice elevation model of the scene. You can also use multiple SAR images, form the interferogram, and then subtract the elevation if you already know it. And in this way, you will see changes in the elevation. So what you see here is not the interferogram as in this example, but what you see is just changes in the elevation. And in this case, it was because they were building, I think, an underground line, a subway, right? And for this, they had to get rid of the groundwater, and then basically parts of the city were sinking through for quite some centimeters. So one fringe is around 3 centimeters here. Right. So you see the whole city was basically sinking by quite a bit. And the last thing I want to talk about is SAR polarimetry. I was already mentioning this a little bit. Here you need to keep in mind that SAR is using electromagnetic waves, right? And electromagnetic waves you can polarize. So in general, a wave can oscillate in all kinds of directions perpendicular to the direction of the wave. And if you polarize it, you're just restricting the way in which the direction can oscillate, right? Most commonly, we do it either like horizontally or vertically, right? So this would be the H and the V. So we would, for example, send out one wave that is horizontally polarized. Then we measure the echo horizontally and vertically. And then quickly after that, as soon as we are more or less certain that we have recorded all the echoes, we send out a second pulse that is vertically polarized, and again measure the echo horizontally and vertically. So this gives us 4 measurements, right? HH, HV, VV, and VH. Right? So we can have 4 images of the same scene acquired quite quickly after each other, right? So there's not much movement of the plane in between or something like this. And then those 4 images we can combine into a color image. If the emission and so the receiving antenna is at the same position, those 2 images here, they are the same up to noise, so you can basically average them. So this leaves you 3 channels, and those you just cast into the RGB channels of an image, and then you can have a visualization like this. Right? And you see different backscattering mechanisms result in different colors, right? So forest area here, it looks very different from surface scattering, for example, over agricultural fields, or here you have some water areas that are black and so on. So this is the information we want to exploit. All right, so this was my brief introduction to SAR. I think I have answered nearly all of the questions in the chat. So rain and snow I have covered, I think, and then there was a question whether more appropriate color representation for single or dual pole SAR. Yeah, I will show one example later on. It's still an ongoing field of research trying to colorize SAR images, mostly for human interpretation. So for dual pole, this means you only have 2 polarimetric channels. What you do mostly for the 3rd RGB channel is you just take the ratio of the amplitude of the first 2 channels or something like this. For single channel SAR, sometimes you try to compute features of the SAR image and try to include this or color code this in a certain way. But it really depends what you want to do with those images, right? Do you want to show them to laymen? So you want that they are very close to optical images, or do you want to emphasize certain scattering effects? So there's not really like one correct answer for this. Even for fully polarimetric SAR, there are different ways to visualize this, right? again, depending on whether you want to make this very, very colorful, because you want to have like a public relation campaign for laymen, and you want to provide very nice and colorful images, but you don't care much about how accurate the information is you display there, or you want to have it for SAR experts that do understand what they are seeing there. So you want to it does not need to be very colorful, but you care more about accuracy. So it really depends what you want to do with this. All right, did I miss any question? Anything else I should answer right now?
Yes, we don't have any question on YouTube.
Perfect. Then I hope I didn't bore the people with my introduction to SAR. I know it was very quick and very much on the surface, but I hope now you have all the necessary buzzwords like speckle, phase, intensity, pulsar, INSAR, a little bit in your head when we now finally talk about deep learning. So let's start with spectral reduction, right? Just as a reminder, speckle was this noise-like phenomenon that was coming from the interference of all the individual echoes that I might have in one resolution cell. And this is really a problem, right? It's really a problem for humans. It's really hard to interpret those images because you have those random fluctuations going on there. But it's even harder for computer vision architectures that are trying to automatically interpret those images. In particular, because most of them are designed for optical images, and in optical images, we do not have that, right? In optical images, we might have additive noise, but speckle is more a multiplicative random variable. So they can't really deal with this. So there's a lot of research going on how to reduce the speckle in radar images. And of course, there are traditional approaches that are doing traditional image processing. But nowadays, of course, there's a lot of very interesting work on spectral reduction via convolutional neural networks. So what you want to do is that we have a speckle image, right? So a normal SAR images with a lot of speckle in it. And what we want to produce is a speckle-free image, right? By putting this into a convolutional neural network. Well, how would you do that? Well, you would, of course, need a training database, right? Consisting of the images with speckle, the images without a speckle. Then you would put this into a neural network that would produce a certain output. You would compare the output with your speckle-free image, compute the loss, and then backpropagate the gradient of the loss to change the network parameters. The problem here is speckle-free images do not exist, right? Speckle is an inherent property of the processing of SAR. It's not like noise in optical images. For optical images, I can make sure that I have a really high signal to noise ratio, right? I just make sure my scene is well illuminated. I have a lot of light. I have a long exposure time of my camera and so on. So in this way, I can make sure that I have an image where there's virtually no noise. There's always a little bit of noise, but let's say virtually no noise. For SAR images, that is simply not possible, right? So we can't really produce this. So the way how people dealt with this is they use an optical database. So in a database of optical images, they produce a grayscale image because SAR images, if you only have a single channel SAR, they are grayscale. And then they have a noise model, right, a statistical model describing the speckle, and they add those two things together. So in this way, they have an optical image with speckle. And this is what they now use for training, right? So the speckle-free image they use as the reference. This would be the input image. And in this way, you're training your deep neural network. And then, of course, you apply it to real SAR images and hope that it works. There are a couple of examples that are doing that, right? It's not just one paper. I only have two here that were one of the first trying that out. But of course, there's a certain limitation to that. An optical image does not have the same geometry as a radar image, as you might remember from my talk before, right? So those shadow areas, those layover artifacts, and so on, they are simply not there, right? A SAR image is not an optical image of speckle, right? So there is a certain domain gap between what you have trained your neural network on and real images. Nevertheless, it works to some extent, right? So here you see the architecture of those two examples, exemplary paper that tried that. It's very much the same. So it's usually like a residual architecture. This means that you try to estimate the speckle and then kind of subtract it or divide it from the image, right, in order to produce a speckle-free version. And it works very well. So for this architecture here you see an example. So this is an original input image. This is a state-of-the-art non-deep learning spectral reduction technique. And this is the proposed method via this convolutional neural network that was trained on synthetic data. People also tried to push this a little bit by using a temporal image stack of real SAR images, right? So here, at least you do have all the effects that you would have in a SAR image because you're really using SAR images, but you're using a lot of them, and then you just temporarily average them in order to get rid of the speckle. And then you're using this reduced speckle image as the target and train your neural network. And that works also quite well, of course. Oops, sorry. But of course, I mean, you need to have this temporal stack of SAR images, and you do not have too many of them. And of course, you cannot just do this for single channel SAR images, but also, for example, for polarimetric SAR images. So this would be an example here where this paper used a two-stream architecture. So you would have the polarimetric SAR image, here a certain representation, that is the polarimetric covariance matrix. So in every pixel, you have a covariance matrix. They take the matrix log so that a multiplicative random variable becomes an additive random variable, right, which is easier to deal with for neural networks. And then they have two streams. The first stream is trying to estimate the despeckled, the clean image, and the other one is trying to estimate the noise. Then those two are combined in the architecture. They are, it takes exponential again to go back to the original domain. And then we have the reconstructed image. And we want that this reconstructed image is as close as possible to the original image, right? And on the other hand, we want that this denoised image is as close as possible to our target image. And also here they use a database where the target image is coming from a temporal averaged image stack. And then you train this neural network, and that works quite well. So here are some results. So this would be a patch of the noisy input image. Those are two traditional methods. This one here is very basic image processing. This one here is a state-of-the-art technique that usually works quite well. And those would be the results of the deep neural network. This would be a real valued neural network, and so is the proposed neural network by the paper that was using a complex valued neural network. Of course, pulsar images are complex valued, and the results improved by quite a bit. All right, so those is the the straightforward approach that you can have for spectral reduction. You somehow have your noise-free training data set, right? And then you just do a supervised approach. But of course, I mean, it's really hard to produce those noise-free target images, right? Either you have to limit yourself to optical images and to some kind of noise model, right? So then you don't have the effects of SAR images in your training data set. So you have this domain gap between training and application, or you have to have a temporal stack of SAR images and a lot of them in order to produce spectral reduced target images. So more modern approaches try to go away from that. They try to use other ideas to get rid of this strong constraints on your targets. So one approach that I like really a lot is called noise to noise. So this comes from computer vision. And they recognize that well, usually what a neural network is trying to do is something like this, right? So you have your neural network F that depends on parameters theta. It gets an input image X, and it will produce an estimate of the target image Y. And then you have a loss function L that is computing the loss of the network output with respect to the target image, right, averaging over all the training samples that you have, and then trying to optimize for the network parameters. Right? So this is what the network training is doing. So what they recognize is that you actually can split this term into these two averages, right? So first the expectation over possible target images over your input image, and then you average over all the input images you have. So those two things are equivalent. Right? Now, very often, this is actually a problem for neural networks because very often this relationship is not one-to-one. A typical example is, noise, for example, is a typical example, right? There are multiple noise-free images that could correspond to a noisy images. Same goes for super resolution, for example, right? There are multiple high resolution images that could correspond to a single low resolution, low resolution image, right? And usually what the network is doing in those cases is averaging over the possible solutions. So you get kind of like a blur. So this is a huge challenge in super resolution images, because if you train this in the naive approach, you would just get a blurry upscaled image. So you need to make a lot of effort to prevent this. Now for denoising, we actually want this averaging over possible, excuse me, over possible solutions. So what they showed in the paper, that actually you can replace this optimization by this optimization, where you replace this here, not with a clean target, but with somehow a corrupted version of the target. And those two things are equivalent with respect to the learned network parameters, as long as the expectation of this degraded target is the clean target, right? So in our case, as long as the expectation over all the noise, so if I would average certain noisy versions of the same image, if I would just average them and I get the original clean image out, as long as this is true, so my noise is not really changing the nature of the image, then those two things are equivalent. So this means that I can optimize my network by this equation, and the network parameters will be the same as I would have obtained by optimizing this equation, right? At least in the limit. But this equation has a huge advantage that here I don't have a clean target anymore. I have a corrupted target, right? That is following a certain distribution. So this is very, very interesting. So people have used this for spectral reduction as well, but let's see some, let's say, proof of this idea taken from the original paper. So what you see here on the x-axis is the number of epochs the network was trained, and here you basically see the achieved accuracy. Once for clean targets, that would be the blue curve, and for noisy targets, right? And you can see that both things converge to the same solution, right? It's the same accuracy, right? No matter whether they have trained the network on clean targets or on noisy targets. So this was for additive Gaussian noise. Here they have chosen a different noise distribution, where the noise is spatially correlated. So those different lines here correspond to different spatial correlation of the noise. You see this here a little bit, right? So you don't have noisy pixels, but you have like whole noisy areas. And you can see that, well, if the spatial correlation is bigger, then convergence is slowed down a little bit, right? This blue line is down here. But at the end, even then, they converge to the same point, right? So the network is learning the same thing, no matter whether you train it on clean targets or on noisy targets. So one version that was using this for SAR worked like this. They are still using optical images, right? So you have a speckle-free version of an image, of course. Then they had a noise model, a speckle model. They produced two noisy images, right? And then they used this noise-to-noise framework, right? So you try to use one noisy image as an input, and you try to estimate the other noise, the other noisy image. And a way to look at this is that it's not possible for the network to predict the noise in the other image, right? The noise is kind of random. So seeing the noise here won't help me to predict the noise here. The only thing that the network can predict is the underlying image structure. And this is exactly what the network is doing at the end. So you get a despeckled image out. Well, and then you can, of course, apply this to real images, right? So for real SAR images. So once this network is trained, you have your speckled image as input, you put it into the network, and you get the despeckled image out. There are different papers that are doing this. This one here I like a lot because they did this for volcanoes. So you will have a very noisy Sentinel-1 image of a volcano area, right? Maybe if I wouldn't have told you this is volcanoes, you would have hardly seen that. And then you apply this noise idea, and you get a very nice despeckled image out, right? So here you can clearly see the volcano. Another idea is taking this even a little bit further. So for this noise to noise idea, you still have to have different noisy versions of your input images, right? So you have to have images of the same scene, but taken at different timestamps, for example. That was done in the volcano example. In the noise to void or noise to self idea, what people try to do is to have a denoising network that is only trained on single images, right? So you don't have image pairs for training, but only a single image. And the idea is, if you have your noisy image, you're masking one of the pixels in a patch out. So this might be a training patch, and you're just masking the center pixel by copying the value of any other random pixel in the image. So for example, you would take this pixel value here and just copy it here, just by masking that. And then you want to use the network to estimate, based on this neighborhood information, to estimate the true value of the center pixel. And so this is the basic idea of noise to noise. And this was also tried for spectral reduction, where they called it speckle to void. And I really like this paper a lot because it's combining two things. It's combining knowledge that we have about radar images with deep learning. And the way they did this was they used a known statistical distribution of speckle. So you can show that under certain assumptions, given an image area, the speckled version of a pixel, this one here, is following this statistical distribution. It's a very complicated distribution, right? But still, at least we have an idea how the values will be statistically distributed if this is really a SAR image. Now the problem, or the nice thing, let's start with the nice thing. The nice thing about this distribution is that we can actually estimate the denoised version of a speckled pixel. So given the speckled version of my image, right, the neighborhood and the pixel value, I can estimate the despeckled version of this pixel value in closed form. The only problem is I need to know those two parameters, right, of my statistical distribution. And of course, I do not know them. They depend on the neighborhood. Now, the idea here was that they use a neural network to learn that, right? So during the training phase, they would have this noise to void network that is estimating those two parameters of my statistical distribution. The training loss would be governed by statistical distribution of my speckle, right? So I can train this network, and then during the denoising phase, my network will give me those two parameters, right? So for each pixel position, it will tell me what kind of alpha and beta to use. I can put them into this equation, and I get out the despeckled version. And this works very well. So the architecture, how they ensured that this masking is happening in the correct way, was that they use orientated versions of the image, put this into the network, where the network, different networks for each of those rotated versions has shared weights. Then you do a couple of processing, then you combine all of them, and then you estimate the corresponding alpha and beta for each of the pixel values. So those are the four streams, right? So this would be the rotated versions. Here you see the receptive fields. So you rotate a little bit, you shift them a little bit, and then you combine. And this gives you this blind spot network, where the network is focusing on this interior part, right, but not on the external part. And here you see some results. So this would be the input image. Those are a couple of state-of-the-art denoising or despeckling techniques that are not based on deep learning. This one here is on deep learning, and those two over here, those would be the speckle to void in two different formulations. And it works really well, and I really like this idea. All right, were there questions for noise? How good are Sentinel-1 images? So Sentinel-1 images are very good. Depends on what you want to do with them. So the resolution is not the best. I mean, it's a spaceborne sensor, but and not a new one, right? So the resolution is not the best, but for many applications, it's actually quite okay, right? It's only dual pole, so you don't have full pole information. That is also very common for spaceborne sensors, because having full pole information puts a lot of stress on the hardware. You need to send out those two pulses in different polarizations quickly after each other. This takes a lot of energy as well, so it's not really a good idea to do this on the satellite. So it's dual pol, okay. But the really good thing about Sentinel is it's free. Anybody can access everything at any time, can just download those images. Same is true for all the Sentinel satellites. And this is really great, right? For TerraSAR, you have to write a science proposal, for example. It's usually granted, but still. Then you can't distribute those images and so on. So this is really the great part about Sentinel. And I do wish that more data providers would do that, right? At least for a couple of example scenes, just put it out for the people to use and whatever they want. This is really great. And I do believe that this pushed the science and remote sensing and also deep learning and remote sensing really forward, because now we have unlimited access to data. Then there's one question: since it is very difficult to find free and labeled SAR dataset, would it be a sensible approach to apply transfer learning from optical imagery to SAR? Yes, it is. I will cover this later in the second part of the lecture today, right? So if your question's not answered by then, just ask it again. How good is speckle filtering options for ASAR Snap? I can't answer that. I don't know what exactly they are doing. I would assume that they do is one of the standard speckle filters, which is kind of okay, but usually for the standard speckle filters, you get rid of a little bit of speckle, but you do lose resolution a little bit. So again, it depends on what you want to do. Is there a pre-processing pipeline for amplitude images? For example, data clipping, normalization. Again, it depends a lot of what you want to do. So usually if you want to do deep learning, you use a log transform on your amplitudes so that the multiplicative speckle is going into an additive variable. You might want to do some clipping because for SAR you have a high dynamic range. So most of the echoes you receive, they're quite small, right? So in the lower decibel range. And some of them, they're really bright. If you have like a corner reflector, what I've shown before, they're super bright. So this means, like a lot of data is in this range, and then you have one that is really like a strong outlier. So sometimes you're clipping those away to not to, confuse your network too much with this. Also, you do like a nonlinear processing, again, like a log transform, not just that the multiplicative random variable goes into an additive one, but also that, the log function looks like this, right? So you have a contrast enhancement for like low intensity areas, majority of your image, and you have a contrast reduction in the high the high reflections, right? So some things like this, but again, it depends a lot on what you want to do. All right, so this was speckle reduction.
Okay, we have one more question on YouTube.
Yeah, go ahead.
Read it. How well these CNNs will deal with topographic distortions such as foreshortening?
Can you say it again?
How well these, I think, CNNs will deal with topographic distortions such as foreshortening?
Yeah, that is a very good question. I would also refer it to the second part of the lecture, because there we will see this a little bit. In general, it's not easy because if you have a high building, the high building is distributed over a large area. Now, if you want to estimate the building footprint, for example, like you need to recognize the building in this area and then infer from this big area, like which small part is the building footprint. But there are approaches to deal with this, and we will cover some of them in the second lecture. All right, then let's continue with the next one, which is phase, right? So now here, just to remind you again, we assume that we have two images of the same scene, and we combine those two into an interferogram, right? So basically, we analyze the phase that we have, right? So a very accurate distance measurement. And what you want to do is you want to produce an elevation model. So, I mean, this is quite easily possible, right? So you have those two radar images, Z1 and Z2, you just combine them in this way. And then, well, you need to normalize this a little bit, but then you have the interferogram. So this is complex value. So the amplitude of this or the intensity of this interferogram is called coherence, and the phase is the phase that is usually visualized in this way. So the problem here is that we have a lot of noise in that, right? We have different scattering mechanisms that are introducing noise. We might have atmospheric stuff that is changing the phase. So the amplitude is quite robust, but the phase is sensitive to some atmospheric things. The acquisition geometry has an influence, right? The baseline you might have, and so on. So the goal of this processing here is that how can we obtain an enhanced version of the interferogram, right? Noise-free, for example, and of course by deep learning. And one nice work by colleagues of mine is called FiNet. So what they do is they do a PCA, basically a projection into the eigenspace based on the real and imaginary part of this complex interferogram in order to obtain A and B. And this is the input to a convolutional network that is then supposed to estimate an improved version, right? So those A and B values here, so the eigenspace of the real and imaginary part of your interferogram goes into a neural network, and what you want to estimate at the end is a denoised version of this. It's again a residual architecture, but otherwise quite standard. So the loss function is really just comparing the estimated A and B values, right, the noise-free ones, with the noise-free ones, right? So the question is, of course, how we get the noise-free ones, right? We will see this in a minute, but otherwise it's just the L2 norm between those two things. The other part of this loss function is just to make sure that the estimates are in the right range of the interferogram. The interferogram is normalized by the amplitude, right? So those two things are between 0 and 1, and this is used as prior knowledge as a regularization term here. Now the question is, how can we get noise-free interferograms? And what they did here was also a very nice trick. They used an existing elevation model, the different regions of that, and basically simulated how the interferogram would look like if it would be noise-free based on this DEM. Right? So this is in those two regions here how the interferograms would look like, right? Depending on the topography. If you can zoom in a little bit, right? So you can have areas where the topography is changing only a little bit or quite quickly. Now you can use this those noise-free interferograms, and you just add noise or also other artifacts that you might encounter during processing of real interferograms, and then you use this again as input and output to your neural network. And the results are actually quite good, right? So if this is synthetic data, of course, but test data, so it was not seen during training. So you might have certain forms of noise. These are different non-deep learning techniques to denoise the interferogram, and this is the proposed method, the FiNet. And here you see the differences between the ground truth. And you can see the results, at least on the synthetic data, are quite promising. But also on real data, it looks very good. So here you would see the intensity of the SAR image. This is the interferogram, so the phase of the interferogram, and this is the coherence. And we can zoom in a little bit in those regions. You see very fine-grained structures. And if you zoom in a little bit more, then we can analyze the noise pattern. So here you would see the optical images of those parts of the SAR images, right? Of course, they are not used in the processing in any way. This would be the input, right? So the real noisy interferograms. So if you just do a simple spatial filtering, so just a little bit of blurring. This is a standard denoising filter or state-of-the-art denoising filter for interferograms. It's getting better, right? So it's better than that one down here, right? Definitely better than the input, but you still have some kind of problems, right? There's still some noise artifacts going on here, and FiNet is producing very clean interferograms that then can be used. All right, so now we have a method that can take those noise interferograms and can produce a noise-free version of that, but we are still not at the DEM, right? We're still not at the elevation model. In particular, we have those fringes going on, right? So one step what we would need to do before we can generate the DEM is compute the absolute phase, right? So what we have are those unwrapped phase, how it's also called, right? It's interferogram where you can see all those fringes. And the reason is, of course, that the phase lies on the circle, right? So I can add 2 pi and nothing is changing. I have the same phase value, right? So if you remember the phase is the angle of this complex vector, right? And if I turn this by 360 degrees by 2 pi, I'm back on the original position. So this is why I have those fringes. And what I would like to have is this absolute phase, right? Where those fringes are gone. And now here, this really corresponds to changes in elevation. So from my interferogram, where here A is again the amplitude, rho is the coherence, and C here is the unwrapped phase. Omega is just a noise term. What I want now is phi, the absolute phase, right? And of course, this is just the wrapped phase plus some kind of multiple of 2 pi, right? So I could compute this very easily if I would need, if I would know how often I need to add 2 pi to that, right? So now the task is to estimate this rep count here. So what they did in this paper was to try to do this with a CNN. They tried to make it a little bit simpler, so not directly estimate the absolute phase from this rep phase. What they did was to estimate the rep count and actually just the change of the rep count. So they were assuming that between 2 pixels, 2 adjacent pixels, you can't have a phase jump larger than 2 pi. This would be a tremendous jump in height. So they assumed that this is not happening. And this means that, you know, this rep count can only change by 1, right? So either it's not changing at all if I don't have, if the height change is within 2 pi, or it's changing by 1. Right? So this change of my rep count here, that is basically just taking 2 pixels next on the left and the right hand side of the pixel of interest, since each of them can only be 0 or 1, the change of the rep count can only be one of those 5 cases. So either it's 0, it's minus a half, plus a half, minus 1, or plus 1. Okay? And then they casted this whole thing as a classification problem. So you have your input interferogram, and what you want to use your convolutional neural network for is to just classify, but based on this input, which of those 5 cases we encounter there. Once we have that, once we have this gradient, we can easily reconstruct this rep count, right? Just by, you know, like going back from the gradient. And once we have the rep count and then the original interferogram, we can produce the absolute phase. So they used a simple unit structure from that, nothing interesting going on here, right? So just like some encoding and decoding with skip connections, that is estimating the rep count. They did this individually for the azimuth and the range directions to do this a little bit more, to ease the situation a little bit for the neural network. And what they also tried is not just to use interferogram, so not just the phase, but also the coherence as an input. And the results are really good. So here you would see the ground truth phase, the absolute phase. Those would be the estimates of the proposed network. Those are some standard techniques to do that in 2 different situations. And this is the error you would observe. And you can see that actually the estimates are quite good. The CNN plus here, this means that also the coherence was used. This one is just using the input phase. And it turns out using phase n coherence is a little bit better than only using the phase value. All right, and I believe with this, we are nearly at the end of the first lecture, right? There are a couple of minutes for questions.
There's one question on the Q&A section.
Mm-hmm.
The spatial resolution of optical image and speckled image in using CNN for producing the speckled image should be equal. The resolution of the image should be equal optical and SAR image side.
Yeah, to some degree, right? They should not be too different. On the other hand, you don't need to be too strict there because, you know, like the difference in resolution is only one of the many differences between an optical and a SAR image anyway, right? As I said, geometry of the objects, for example, will be very different. So you need to be more or less in the same ballpark, right? So I would assume if you train your neural network on speckled versions of optical images that have like 10 centimeter resolution, and then you apply it to a SAR image that has, I don't know, like 10 meter resolution, then probably you will be in trouble. But yeah, if it's more or less in the same range, I would think that the other artifacts, the other parts of the domain gap will be much more severe than the small change in resolution. But yeah, you're right. I mean, in general, the closer you can get your optical images to the SAR images, the better it is, right? Same goes for semantic content, for example, right? So if you train on dense urban areas with your optical images, and then you apply it for agricultural areas in your SAR images, this will also be a problem.
Okay, I have one question. What do you think about the autoencoders?
Autoencoders are really good. It's a really nice idea. I will have a couple of examples later where they are used for pre-training neural networks. So autoencoders are quite nice. In a way, you can see this noise to noise as an autoencoder. It's not auto because you're not autoencoding X to X, right? But two different instantiations of X, right? So you could say it's going from one noisy version of X to another noisy version of X. So in a way, it's also an autoencoder on the true image. There's another question. One of the problems is saturation in above ground biomass estimation works using radar images. For understanding better saturation of radar signals over forest and solution of these problems, what do you recommend about it? Whoa. All right, so let me see. So biomass corresponds a lot on forest height, if I'm not mistaken. So I'm not an expert there, but as far as I understand, you would take your radar images, you would try to estimate the coherence based on that, the volume decorrelation that correlates to your forest height, and forest height corresponds to biomass. Now, all of those things come with approximations and certain assumptions about the underlying forest you're looking at, right? So one idea would be that you use not just the input coherence, in a single pixel, but also the surrounding, maybe even the intensity of the radar images to solve for some of those parameters in a better way, right? So that you can adjust your physical models to the actual forest that you have in this area, so that you can spatially varying physical models that are then estimating forest height and biomass. The other thing what you can do is you can try to use a machine learning approach or a neural network to directly estimate the biomass if you have enough data to train this. If this information is contained in the data actually, right? So if this information is not contained in the data because the data itself is saturating and not just your model estimates, then you're lost, right? Then you can't estimate this, at least not completely.
Yeah, I think we don't have any other question. Then I would like to thank Ronny for this very informative talk, and we can close this session. And next session will start at 11:30.
Just an update, we'll be staying in the same Zoom webinar session, and the same YouTube live stream will continue. We're just giving a short break while within the same session.
Then see you.
All right, thank you. Then see you in 10 to 15 minutes. I hope you enjoyed it so far. All right, should I continue then, or do you still wait for a minute?
I think you can.
Yes, we can continue.
Okay, great. All right, then welcome back, everybody. I hope you refreshed yourself a little bit. So in the first talk, I covered a brief introduction to SAR, right? And then we talked about spectral reduction and interferometric phase. So this was both more like image processing, right? So how can we take a SAR image or a product from a SAR image and produce an enhanced version of the very same product, either a speckled-free version or at least despeckled version, or an interferometric phase and coherence that have less noise. So in the second part of my talk, I want to talk about how to use deep learning to do information extraction from SAR images. So not just enhancing the quality of the product, but really deriving at a different product. And I want to start with parameter estimation. And there are surprisingly less works doing that. There are some out there, but not so many. So the one I decided I want to cover here is doing something very interesting. It's in a way physical parameters, but special ones. You will see what I mean in a minute. So the idea is that we have a SAR image, a real SAR image. We have a network, and this network is extracting physical parameters of this image. Right? So this could now be like anything, right? But what they did in this work is that what they were estimating here are physical parameters that then can be input to a simulator that is simulating SAR images in order to increase the realism of those simulation images. And then those simulation images, they can be used, for example, for data augmentation or to check how the object is changing with different angles, for example, different look angles of things like this. One of the simulators they were discussing in the paper, it's not the one they at the end then used, but comes close enough, is RASAR. It was developed by colleagues for me at the DLR. It's based on PLV array. And here the idea is that you do have a 3D model of your object, and you basically do ray tracing. So you follow the rays from your sensor to the object, how it interacts, and then how it comes back. You have a certain signal model, of course. So, for example, that's supposed to be specular backscattered signal might be described like this, where you have certain object properties. You have the intensity of the incoming signal. This is describing the object geometry, so like the surface normal and basically the viewing direction of the sensor and another reflection property of the object. So there are several of those reflection properties of the object that you need to specify in order to get realistic SAR images, right? If you do, the things that come out are quite interesting, right? So this would be a simulated SAR image of the Eiffel Tower in Paris, and this would be a real SAR image. And you can see that, the main parts are quite well covered, right? So you have the shadow areas, right? You have the bright areas in the right positions and so on. So the challenge, of course, here is how do you set those properties correctly, right? You do not know that. You don't know the spectral reflection coefficient of an arbitrary object in your SAR images. And this is where this paper came into play. The way they solved this was that they used the simulator in order to map input parameter to simulated images. And then they used that in order to train a neural network. So they would put the simulated images into the neural network. The neural network is estimating the simulation parameters. They are compared to the true parameters. You compute the loss function, and then you backpropagate the error. Now, they experimented with different models. The one that worked best at the end was a GAN architecture, a conditional GAN architecture, where you have a generator. You put your input image, your simulated image during training into this generator. The generator will produce or will estimate the simulation parameters. And then you use the simulated image together with this, the estimated parameters in a discriminator, and the discriminator needs to decide, is this, given this simulated image, are those parameters real or not, right? So you train the discriminator with either estimated parameters or the true simulation parameters, and the discriminator needs to decide whether it's real or fake, right? Estimated or the true ones. And the error that this discriminator is doing is backpropagated into the generator. So you're basically telling the generator how to change its parameters to produce the output that is confusing the discriminator. That's the basic idea. And then you train those two networks against each other. And this worked very well, right? So now you can use this as a CNN, the GAN architecture, the generator basically, put a real SAR image in, and then what the generator of the GAN will tell you is what kind of surface parameters are present in this real image. And then you can use those surface parameters as input to your simulator in order to simulate more realistic images of this object. And you can use those surface parameters also when you vary different properties of the object, for example, the look angle and stuff, things like this. So they proved in the paper that the realism of the simulated image is increasing by doing that. It's better than just adjusting those parameters by hand. They also experimented with a standard ConvNet, so without the discriminator, and showed that the GAN is actually better, right? It's improving more the realism as a standard ConvNet. So this is one example of how to extract physical parameters from SAR images that I found quite interesting. Another one is estimating the sea ice concentration over land and ocean, mostly ocean. Sea ice, it's ocean, but you can have portions of land in your image area, of course. So this is a study area they used in this paper, but it's not the only paper that tried to do that. They used a quite standard convolutional network, right? So we have a couple of convolution and pooling layers at the end of fully connected layers. So it's a standard ConvNet. They used radars at 2 image areas during melt season, and they just used those images. So there was no pre-processing or feature extraction going on. And they showed that this actually works quite well. So this is the estimation of the sea ice over the training data, right? So here it's not surprising that the network is performing well, but even over the test area, it's performing also quite well. Not as good, of course, as over the training area. It's usually the case for machine learning, but still good enough to be useful in practice. So they showed that the mean area. So the mean error compared to manual interpretation is around 10%, right? So you're around 10% different from a manual interpretation of the images. But you can produce ice concentration maps with a lot of details, right? And it works reasonably well, even in very difficult areas. For example, areas where you have melting going on or you have a very low ice concentration. So this is how the concentration maps look like. So this would be a manual annotation by sea ice experts. This is a standard technique that is used in practice, and this is applied ConvNet. And you can see that they are very much in agreement with each other. This is another example for extracting physical parameters from pulsar data. Here it's about extracting soil moisture or soil permittivity, to be more correct. So we have a small part of a SAR image, right, over here. It's a pulsar image acquired by the FSAR sensor. And in this area that is marked here, we actually had in situ measurements of soil permittivity. So there were buried sensors that were measuring soil moisture at different levels. So in this way, you could produce a map of soil moisture in this area. So blue means dry and red means very moist. So in this work here, we actually didn't use a deep neural network, but a random forest, but also a specific random forest that very similar to deep neural networks is learning the features directly from the data. So not this shallow learning that is, you have your feature vector and you put it in, but this is a random forest variant which works directly on the data and is also learning the feature by itself, as the deep neural network would do. What you see here on the top are 2 different physical models. So this would be the estimate of the physical model, and this is the difference to the reference data, right? So the difference to this. Well, and you see, well, it kind of works, right? So you have this dry area here, but there's a lot of underestimation going on here. This is another physical model that is a little bit informed. So here you have different parameter estimates for different moisture levels that you know a priori, right? So it's a little bit informed. And it works, of course, better, right? So in particular, this area improved, but also the area top here. And this is the area, this is the estimate the random forest is doing directly from the data. So a direct estimate from the polar image, a direct mapping from the polar image to the soil moisture estimate. And it also actually works quite well, right? But the real performance increase comes when we combine those two things, and that is quite interesting. So what we did here is we used the estimate of the physical model as an additional input map for the random forest to choose from. And this is how we achieved this map, right? And this is very accurate. The only part where it makes mistakes is down here, where it has this really high soil moisture. Really high soil moisture is difficult to estimate even from the physical models, but it might also be that this might be like a sensor misalignment or something like this. And it turns out that when we're combining those different things, the error that we obtain, this is shown here, is the lowest from all the different combinations, right? So if you only would do physical model, the errors are much higher than combining physical models and machine learning. All right, I think there was no question. What was there? No, none that I see. Okay, great. So this is just a few examples how you can estimate physical parameters from SAR data, right? It's not all of them, of course, and for each of them just a small example, but just to give you an impression. So the next part will cover something that was already a little bit asked before by one of the participants. How can we combine SAR and optical data, right? And well, one of the big challenges if you do this is you need to align this data up front, right? You need to make sure that the pixel in the optical image and in the SAR image shows the same thing, right? And this is really hard. So here you see a couple of examples. So this would be two SAR patches from TerraX, I believe. And this would be optical patches of the same scene, but seen from different angles, right? And you can see it's really not easy to align that, right? It's actually quite hard. So in this work, what they were aiming to do is to write a deep neural network that presented with two patches, a SAR patch and an optical patch, decides whether they show the same area, the same object. They used TerraX data, 1 meter resolution, and an airborne system from using an ultracam with 20 centimeter resolution. Their training set had around 30,000 SAR patches and around 90,000 optical patches corresponding. It's more because there were optical images from different looking directions, right? So one SAR patch corresponds to multiple optical patches. And they aligned this in 3D. This I will cover in a minute because it's quite interesting how they did that. All right, so now what they have as training data is those matched patches between SAR and optical. And then they used a two-stream neural network where on the one stream the SAR data goes in, it's getting processed a little bit by convolutional pooling layers. And the other stream, the optical data goes in, it's also processed by a couple of pooling and convolutional layers. Then we have a concatenation of that. Again, a little bit of processing going on. And then here at the end, we decide whether those two patches do correspond to each other or they don't, right? And then you train this thing. Here you see a couple of results. So this is when it's correct. So those two patches do belong to each other. They do show the same thing. This are true negatives, so they do not belong to each other. This is false positive. So the network shows the same thing, but actually they don't. And this is false negative. So the network does not show the same thing, but actually they do. So you can see it's quite challenging, right? Challenging, but actually it works quite well. So they really get a high accuracy with a low false positive rate. So this is working quite nicely. And of course, this was estimated on test data. So, but the problem with this is it's a nice first step, right? It tells you whether two patches show the same scene or not, right? But this is only the first step, right? The next step would be to finally align those images, right? You might have a small offset between those patches. And this fine registration is even harder than the task before, right? Because here we really want to know the transformation that is necessary to align that. And the problem is, of course, that the image geometry is very different, right? So here you see corresponding patches, right? So this is the same scene, right? So this building here is this thing here. Right? This building here is this here, right? Range is, of course, here, right? So the layover is going in this direction and so on. And now the question is, you know, like, are they aligned? Are the footprints of those buildings at the same position, for example, or not? And how much do we need to shift this? So what they did in order to produce this data set that was used by the different method is based on point clouds. So for optical images, you can use multiview stereo or photogrammetry in order to estimate the 3D geometry. So here the idea is you see the same object from from multiple different look angles, so 3 of them here, and you can use the information you have about the camera positions and in general about the camera parameters to basically make an intersection of those viewing rays to find out the 3D points. And you can do this with aerial images, and then you have a point cloud that is corresponding to the 3D structure of the scene as seen by the cameras. Now for SAR images, you can do something slightly different. That's just, a processing mode of SAR I haven't mentioned before. It's called tomographic SAR, TomoSAR in short. And what you try to do here is to focus in the height direction, if you want. So all of those points, if I have explained before, they would lie on the same pixel position because they have the same distance to the sensor. But now if you have multiple images with slightly different positions, those positions will also change, right, towards the sensor. So you can combine all of those images, this tomographic stack of SAR images, in order to produce a point cloud. And that's what they did in this paper. Now they have 2 point clouds, one point cloud from photogrammetry and one point cloud from TomoSAR. And then they try to align those point clouds. The first thing is they have a rough geocoding, so the point clouds are more or less obtained. Then they project the TomoSAR point density to a 2D image, right? Because the TomoSAR is, as you can see here, it's mostly seeing the facades, right? You have a side-looking architecture. So the point density is projected down towards the 2D plane. And for the multiview stereo point cloud, you produce edge maps where height is changing. So you have those 2 things. And now the next step is that you align them. You just co-register them, just a computer simple correlation. And you know the peak in this correlation will be at the point where you need to apply shift. And then the height alignment, once you have done this, the height alignment is done by ICP, iterative closest points, which is a standard approach to align point clouds, and works quite well if you have a first rough alignment. So this is how they aligned those point clouds. So now they know exactly which 3D point in the photogrammetric point cloud corresponds to which 3D point in the tomographic point clouds. And for both of those point clouds, they also know to which image parts those points belong to. And this is how they can align the patches in the 3D space. So this is really a nice idea, and this is quite involved regarding the processing. So here you can see an output. The green color is the optical part, right? So it's mostly the roof area, right? This is a part of Berlin, by the way. This would be the Sony Center. The landlord of my old flat while I was living in Berlin had the office here, right? The red and blue are points from the tomographic processing from an ascending and descending path, the different directions of the satellites, and you can see it mostly corresponds to the facades and also to the roof structures. So this is used in order to align the patches that then have been used for estimating the correspondence in the other paper. Okay, so but now we still need to estimate this shift, right? So here the goal is that we want to know when we have a SAR image and an optical image, how can we estimate those small shifts to align them? And one application for that is that usually the SAR images have a very, very good geolocation, because this is needed for the processing of the SAR. For optical images, they also have a good geolocation, but not as accurate as for SAR. So what we want to do is we want to align the optical image towards the SAR image in order to improve the geolocation of the optical image. What they did in this paper here was that they used the confident to do this with manual aligned patches. And then the target variable was, of course, the image shift. So you would have a small optical image as input. You would have a larger SAR image where you can shift the optical image around. So this is how you know the shift, right? So I can take this optical image and just put it here in this corner. And then I know that the shift is a little bit in that direction. So this is the output of my neural network. I have two streams. One is taking care of the optical image. One is taking care of the SAR image. And then I estimate the corresponding shift. All right, and again, well, it works not surprisingly quite well. So here you see some results. So the first column here is the optical image. The last column is a corresponding SAR image. And what you see in between are, well, the score maps where bright yellow means a very high score, blue means a very low score. So what you would like to have is a single very high peak. And since for those patches, they are aligned so that the center value is the corresponding pixel, you would like to have this peak in the center of this. So this is the confident solution, right? So you can see, yeah, we have this one single peak in the center, so it's working very well. In this case, we have two peaks. One is in the center, and the other one is a little bit distributed in that direction. And that is because we have like a road here, right? And then, well, you have a certain uncertainty how to shift it in this image. And the other two are two standard techniques, normalized cross-correlation and Bushel information. It's two standard techniques to do image alignment. And the confident is outperforming those standard techniques. And you do direct alignment between the SAR images and the optical images. One problem here, one limitations where they're currently working on is in order to make this alignment good, you need to have a certain patch size, right? The larger the patch size, the more context information you have, the better you can estimate the alignment. But if you have a large patch, it also takes a lot of memory. And I mean, confidence are always trained on a GPU, and GPUs usually don't have so much memory. So you need to find a trade-off between how much data you can put on your GPU and how big the data can be. But otherwise, it's working quite nicely. Another idea to do this alignment, which I find quite out of the box thinking, is this paper where they basically said, okay, cross-sensor matching is really challenging, right? So we have a SAR image and the optical image. Both are very different from each other. So it's very hard to find the matching score. So the solution is we take one of them and transform it into the other, right? Not geometrically transforming, but radiometrically transforming. So either we take the optical image and we produce a radar image, right? Or we take the radar image and we produce an optical image, and then we compare those, because for this, then the patches are the same, right? A synthetic radar and a real radar, and they are more similar to each other, and then we can use any kind of standard matching technique that we want. So they decided, they tried actually both, but they decided at the end to use the optical images, put them into a neural network to produce something that looks like SAR. And then use the real SAR images and then use the matching between that instead of transforming SAR into optical. Well, and this network here is again a conditional GAN, right? So you have again this generator and the discriminator, right? So you have the generator that is taking an optical patch and is producing an artificial patch and then compares them. Right? And then you have the discriminator that needs to decide, well, is this real or not? They experimented with different losses, different batch sizes, different target images, for example, doing despeckling or not, and estimated what works best. So here you see three of those setups. This would be the optical image. This would be the real SAR image. This version here is despeckled, so this is why it looks a little bit different. And this is the artificial SAR image that is produced. So this one is with speckle, right? So somehow the GAN is also learning the statistics of the speckle and it's just adding this on top of it. Here it's learning a despeckled version, and here it's basically learning a speckle-free version that is looking closer to the optical image, but has the same information content as the SAR image. And at the end, it turns out that this is working the best. Although the difference between the synthetic SAR image and the real SAR image are bigger, but the differences are mostly in the speckle. In the speckle, you can't align anyways. But the image structure, there the similarity is the highest in this case. So at the end, they ended up using this setup. And again, it works quite well. So here you see the score maps, the same as in the previous paper, right? Here for the real optical and real SAR, right? So you have a big smudge over the score for the shift. And here you see the real SAR and the fake SAR, right? So same SAR content, but without speckle. That was the idea. And again, you have a very nice maximum at the center. So this works very well. They tried it, as I said, the other way around as well. So taking a SAR image and producing an optical image and then aligning this. The image synthesis also worked, but the alignment didn't work that well. So it worked better in this way. And here you see that here there are like 3 standard corresponding techniques, which produce a certain error. And basically you're reducing this error by half if you do this transformation wire again up front, and then you use the same technique. Using SAR images to producing fake optical images has another application, and I want to mention that here. It's sometimes sold as that now we have an optical sensor that can look through clouds, but I would be very careful with this. So the idea is you take a GAN, so this looks very complicated, but it's just a standard GAN, right? The GAN the generator takes the SAR image as input and the corrupted optical image, corrupted by clouds. Well, then you have your generator, right? So encoding and decoding, and at the end you have a cloud-free image. And then you take this into your discriminator, and the discriminator needs to decide whether that is real or synthesized. So standard GAN architecture. And it works quite well, right? So this will produce optical images with no clouds. The problem here is that if information is missing in the optical image because it's obstructed by cloud, and it's also missing in the SAR image because it's simply not shown in the SAR image because the resolution, for example, is different, then what the GAN will do is it will hallucinate this information. It will just invent something. It will look real if the GAN is well trained. It will look really real, but it has nothing to do with the original image content. One example could be the color of flowers on agricultural fields, right? This is something, you know, whether the flower is blooming or not, that is something you probably don't see in SAR. You see very strong in optical data because the color is changing. You know, if this is obstructed by the cloud, then this information is missing in the optical image, of course, the cloud, and in the SAR image, because SAR doesn't allow to see colors. And then what the GAN will do is the GAN might have understood that this field needs to have a color, and it will put an arbitrary color there, not necessarily the color that this field had at this moment. So this is very, it's getting very hard to interpret that, right? Because some part of the data will be hallucinated, other part of the data won't, and you don't know which one. So you need to be careful. But apart from this, it's working very, very well, right? So here is a cloud-free version. Those are 2 versions that the GAN was producing, one with only taking the multispectral image as input and one taking the multispectral image and the radar image as input together. The visualization looks quite the same, but for the multispectral data, you can show that using the SAR image is producing a smaller error in the different bands, actually. So it's working well, but as I said, you need to be careful with interpretation. All right, what are questions to this? There was one, instead of the case of soil permittivity estimation, is it possible for the case when the soil is covered with trees? Yeah, thank you. That is something I forgot to tell you. So the physical models that had been used in this example are actually physical models that are trying to decompose the signal into a vegetation and a soil component. So you try to take the vegetation component out first and only use the soil component. However, the vegetation model that is used there is a grass cover, right? So you try to take the grass out. If you have high vegetation, then probably you do not go this deep into the ground to really have a reliable estimate of soil moisture. Well, if you do, you need to have, you know, like a different vegetation model for sure. But we do assume that the soil is covered by vegetation. In this example, grassland. Okay, if there's no other question, then we come towards the next section. That is now really doing semantic analysis of SAR images. Before I go into that, I want to make two notes. The first thing is a lot of papers you will find doing semantic analysis of SAR images with deep learning take a standard computer vision or machine learning approach, they tweak it a little bit, and then they apply it to SAR. Right? So there is no novelty, no real adaptation of the method towards SAR. On the contrary, very often the SAR is adapted to the statistics of an optical image. So you would, for example, not use a SAR image, but you would use a visualization of a SAR image as input, because the neural network they are using, they are expecting 3 channels because they are designed for optical images, and optical images have 3 channels, right? RGB. I won't cover those approaches in this tutorial here in this lecture, because, you know, I mean, it's a valid first step. I'm not saying you should not do this, right? It's a good thing to take a method that is working in one domain and checking whether it's working in our domain. So it's a nice first step. It also shows whether certain ideas are transferable from one domain to another, others are not, right? So it's okay to do this. It's just not, for me personally, not very interesting and exciting, right? Because there's no SAR in it. The SAR is just by chance there. It's exchangeable. I could do the same thing with hyperspectral data. Right? So that's why I won't cover that here. The other thing is the evaluation. Many of the SAR data sets, they're designed for shallow learners. So they are, for example, only have like one small image. And this data is not really sufficient to train and evaluate deep learning methods. So I see a lot of papers that are still using very outdated data sets, a lot in hyperspectral imagery, but also in SAR actually. This is really dangerous. It leads to biased results if you do not take this into account. Okay? So there you need to be careful. And what I mean with this is that you're working on a multi-site scenario, right? So you're assuming you train a neural network at one area and then you apply it to a different area, right? But your training and evaluation scheme is based on a single image, right? Because this is the data you have available. Here you see some 2 very standard data sets, the Flevoland data set and the Oberpfaffenhofen data set. Now, this is a problem first because your train and test data are very similar to each other, right? It's the same sensor, you know, it's the same time of the year. So the weather is the same, you know, either it has rained before or not, but it will be the same in the image. This is very unrealistic for your application, right? In your application, you take data from one area, right? Maybe it has rained the day before, and then you apply it to the different area where maybe it has not rained for 2 weeks, right? So, you know, in your application scenario, you will have a much higher variation. So it's very dangerous to do this with deep learning approaches because deep learning approaches will stick very, very closely to the data. The other thing is, the other problem is that usually when people do this, they train and evaluate on the same data, they do it like this. So they have their input data. Sorry, this is in hyperspectral data, but it doesn't really matter, it transfers to SAR data as well. You have your reference, and then you take a random subset of your reference data for training. So you would train on those pixels, and then you apply it to the rest. Right, so you say I'm safe because those 2 sets are disjoint, right? So this is truly unseen data by my machine learning approach. But the thing is that most of the confidence, they have receptive fields, right? So they would not just use a single pixel as had been before in SAR as well as in hyperspectral data. They would use a rather big area around it, having seen a lot of this data in this surrounding. Right? So there's a strong correlation between the samples that you have in your training data and in your test data. And the neural network will strongly focus on this correlation because this is a really strong signal, and the neural network will discover that and it will use it. Now in your application though, you apply your trained neural network to a different area. So there you don't have this correlation going on anymore, and then the whole thing will fail, right? So this is really, really dangerous. And I showed this at the last IGRS on this data set, just as an example. It's from the data fusion contest from 2018, where we have reference data in the small area here. So here I can sample my training set, and I use the rest of the samples that have not been used for training for my internal test set. And then I also have reference data outside here, which I refer to as the external test set. And then what I was doing was I trained a model, 3 different models actually, on the internal test set, on the internal training set, and I evaluated also on the internal training set, test set, right? So those would be those curves here. And you see those 3 methods perform very well. In particular, this blue one leads to close to perfect performance on unseen data, right? Just trained on data from the internal set and then was tested on the remaining samples from this area. Now I apply the same method to the external test set, and the method breaks completely down. It does not perform at all, right? So this is the standard evaluation approach, right? Evaluated on test samples, not seen by the machine learning approach. It leads to perfect performance. But if you deploy it and you apply it to a different area, right, just a little bit outside of your training area, it breaks completely down, completely useless. So this is really, really dangerous to do. It's already very dangerous to do with shallow learning approaches, and even more dangerous to do with deep neural networks. So with deep neural networks, you should really go away from this one image train and evaluation scheme and go to multiple images. This is really important. All right, but now let's talk a little bit about semantic analysis, and let's start with object detection and recognition. So this is one of the standard data sets in the field. It's called the MSTAR benchmark. It's expand SAR images of military vehicles. So we have armored carriers, tanks, rocket launchers, and things like this, seen from different look angles as well, right? So it's a very interesting data set, and it has been extensively used for deep learning. One of the papers did something very simple. They derived a standard ConvNet. They sold it a little bit as something novel because they don't have a multi-layer perceptron at the end, so there are no fully connected layers. It's just convolution and pooling, right? So you convolve, you pool, you convolve, you pool until the images are small enough, and then you basically have your label distribution up here. So it's rather a standard convolution network, right, where you put in your MSTAR data set, you train, and then you evaluate on the remaining images. And this is the results they get for the different classes, right? So those abbreviations here stand for different tanks, for different carriers, and so on. And this is a confusion matrix, right? So here you would have the total accuracy, and they achieved 99% accuracy in this case. So basically, this means this data set is solved, right? This was for the simple case. There's a more complicated cases where you would assume, you train only on certain look angles, and then you apply to different look angles or something like this. So those are those 2 columns here. But as you can see, even there, they achieve like 99%, 96% performance. So this means basically this data set is solved, right? There is at least one method, and this method is 5 years old, that is achieving 99% performance on this data set. The reason is that this data set is rather easy. There is also a little bit of problem with the background of this data set. So there's actually information contained in the background and not just in the signatures of the objects and stuff like this. So this data set is solved, but still there is ongoing research where people evaluate on this data, right? And try to push the next few percents out. This is really dangerous. Instead, go to a different data set that is more complicated, where you can have a real computation, because otherwise you're just overfitting on this small and outdated data set. So go to multiple images and go to modern data sets. All right, but then, well, in this paper, they also use this network and then try to do an object detection, and it also works quite well, right? So here, if you have a bigger SAR image, you can think about where the sensor was flying, right? Maybe you can answer this now when you're a SAR expert. So was the sensor looking in that direction? Was it looking in this direction? And then you might notice a problem, right? Because this looks like shadow from the trees, right? So it goes either in that or in that direction. And if we look at the shadow of the object, it's going in a different direction. This is because those objects were artificially placed in this background scene and then tried to be detected. And they showed that their approach also works for this object detection. All right. Another big part for object detection is ship detection. So here we want to detect ships in harbors or on open sea. And the problem is, of course, well, you only have sparse data for that, right? There are not millions of images of those ships. So one way to deal with sparse data is that you try to pre-train your network on a different task where you have more data. Actually, that was a question before from one of the participants. So this is exactly what they tried here. And they tried it in two ways. They said, okay, on the one hand, we can have a ship detector that is trained on optical data. So I have an optical data set where ships are marked, and I train my detector there. And then I apply it to SAR images, maybe fine-tune it a little bit. And the other one is that I have a different task. Here they used matching between optical and SAR images. So for this, I don't need to have any semantic information, just the images. I train my matching algorithm, and then I transfer part of the network to my detection problem. So the second part is obviously more interesting, right? So you have a SAR image, and you have an optical image that are aligned to each other. And you try to estimate whether they are aligned or not. So in this way, you can train this neural network without any kind of semantic information. You only need to have aligned data. And then you transfer part of this network into your ship detection problem, right? Because you would assume that if this network can solve this task, it has learned meaningful features, and those can be used here in order to solve the detection task. They used a specific architecture that is called the bridge neural network, where you start with SAR images on the one hand, right? You have positive samples that are aligned to the optical and negative that are not aligned. And from the other end, you're starting with optical images, right, of the same scene, also with positive and negative examples. So those two networks, they can have different architectures. In this paper, they had an identical architecture, but the weights were not shared, right? So they could learn different things. The outcome, however, here, this representation was supposed to be close to each other. And then for positive examples, you know, the difference between those two representations should be small, right? Then it's mapped to 1 or 0. And otherwise, the difference between those two representations should be big. And this network, you can train only on aligned images. And then you take this part here, the SAR part of the network, attach your detection layers up here, and then you have a ship detector. So they tried those two approaches. So the OSD is the optical ship detector just applied to SAR images, and the OSM is the optical SAR matching ship detector, which was pre-trained on this matching task. Both of them works quite well, but sometimes one works better than the other. So the optical ship detector worked better at sea, while the matching, the one that was pre-trained on matching, worked better at land. So they decided that they do both and just fuse those two things together. So for one SAR image, they would have one detector based on the optical ship detector, one on the one that was pre-trained for the matching. Both of them would give results, and then they do a weighted fusion scheme where the weight is proportional to the confidence score of the detections in order to derive the final image. And that worked quite well. Right. Apart from you know, cars or vehicles and ships, another type of objects we want to detect are buildings. Here we go slightly to semantic segmentation, right? But let's handle it here nevertheless as an object detection. So what you want to do is, given the SAR image, you want to know what is the building, right? Where is the building area? Maybe only the footprint, but maybe also this whole area here. Right? And you see the difficulties, right? You have this huge layover areas. The other challenge is how to label this, right? So if you have a dense urban area where you have a lot of high-rise buildings, how do you really label the building area manually, right? I mean, you can see that here's a building, okay, but where does it end? You know, that like, does it end here or does it end here? This is really, really hard to do, right? So in this paper, they did something interesting again, to use tomographic SAR in order to derive those labels automatically. So they have this tomographic point cloud, right, estimated by TomoSAR. So this is again Berlin. This is the Tiergarten, so a big park in the center of Berlin, where you don't have tomographic points, and the rest is dense urban area. The one we have seen before with the Sony Center is here. And what they also use is GIS information, or OSM, OpenStreetMap information. So footprints of the buildings. So they have this TomoSAR point cloud where they know, you know, the 3D structure of the buildings. They do have the footprints from OpenStreetMap. Now, that means they can decide which points of the tomographic point cloud belong to a building. And they also know which points in the tomographic point clouds belong to which point inside of the image. And this means they can automatically label the image areas, including the layover, inside of the SAR images. And in this way, construct the training database. Then they put this into a convolutional neural network. It's a little bit special. So you have your convolution and pooling layers going on, computing the features. Then they attach a conditional random field in order to do some smoothing. They cast it as a recurrent neural network so that they can include it here. And then they train the whole thing end to end. And it works quite well. So they have like a 94% of accuracy of the detection results over Berlin, right? And here you see some examples. So here would again be the Tiergarten, right? It's a big park in the center of Berlin. Of course, there are no buildings. And here's a more dense urban area. And those are the corresponding estimation. All right. The next paper is trying to do something similar, but they push this even further in two ways. The first thing is that, as you can see here, buildings are labeled in green, right? So whenever a pixel shows a building, it's labeled as a building. No matter whether it belongs to the same building or to a different building. Right? So here in this paper, they try to even distinguish different buildings inside of the scene. Right? So every building should get an individual label. And the other idea they say is that this amount of prior information they want to use, they also want to push this forward, and they use GIS footprints as an additional input for information. So not just in order to form the training database, but really as an input to the ConfNet. And they do this in a quite smart way. All right, so the challenge, of course, is that you have those layover areas, right? So here the building areas are marked in different colors, and you can see for high-rise buildings, so for example, this guy over here, right? There's an overlap between this building and this building here, although the footprints, what you can see here in the third column, are far away from each other. Right? So the building footprint is down here and up here, but the building area is actually overlapping by quite a bit. So this is a challenge. So how would you label this, right? I mean, this area here belongs to both buildings. So what they did is they used this information in order to build their training database. So they had a digital evaluation model where they extracted the individual buildings together with the rooftop and the facades, and they also had the footprints, right? So in this way, they could extract individual buildings from individual building masks, the footprint information, as well as the facade information. Now they can project this into the geometry of the SAR, right? So they can find out where the footprint is inside of the SAR image, and also where is the facades inside of the SAR image. And by this, they can produce different masks of the building area, so including the layover, but also only the footprint, right? And they also experimented by only using part of the footprint that can actually be seen by the sensor, right? So the back part can't be seen by the sensor. So they use this as well, labels, but also as input information for the neural network. So on the one hand, they're using the SAR image that is put into the neural network, right? Standard ConvNet, again, convolution pooling, and so on, where you want to predict the buildings at the end. But they also used the GIS information, in particular, this part of the footprint that is visible for the sensor. And they use this in order to basically normalize the feature maps that are computed here, right? So this footprint tells you how, where this position, where is the position of the building? How is the position localized in this image? So this is how they want to use it. So they want to scale and translate those feature maps a little bit, right, for the different scales. So the way how they do this is that, well, they have this scale and shift function, right? So this would be the input feature. It's scaled a little bit and translated, shifted, and this would be the output function. And now those factors here, again, this scaling factor and the shift factor, they are estimated independence of the building footprint. So they have a part of the network that is taking this building footprint as an input to estimate this scale and shift parameters, and then they use those learned parameters to scale and shift the learned feature maps. Found this quite interesting. So this is basically this part down here, right? Done for the different scales of the different features, and then this way they can produce the output building maps. So this is how it looks again over Berlin, right? So now not everything is labeled in one color if it's a building, but every building has its own color. And now since we have that, and we also have the building footprints, what we can do is actually we can estimate the height of the buildings based on the layover that has been detected, right? So if you have a big layover that corresponds to a high-rise building, right? So you can see this, for example, down here. So there's a layover area here, and it's estimated as a high-rise building. Right? So here we are not just extracting the building area anymore. We're only using the footprint, but we use the extracted building area to estimate the height. And this is working surprisingly well. So I was quite surprised by the accuracy. So here you see the error distribution. It's I don't know, the majority of the error is between ±5 or something like this, which is really nice from a single SAR image. All right. Any questions so far? No. All right. Then let's finally go to semantic segmentation. So for semantic segmentation, or in general for convolutional neural network, the SAR community faced one problem. The convolutional networks were designed for real-valued data. The standard MLPs, they were expecting real-valued feature vectors. The ConvNets were expecting real-valued images, right? All the development that was going on in this area was for optical images, right? And optical images have real values. SAR images, however, they are complex valued, right? In every pixel of the SAR image, we have a complex value, and there is information in this complex value, right? So how can we deal with that? And the early approaches made their life easy, right? I mean, somewhere you need to start, and they said, okay, then we take our SAR image, we extract features from the complex value SAR image, and then we have real valued features, feature images, and we put those into the standard ConvNets. So this is one example where you would extract different kind of features. This is even standard image processing, like gray level coherence matrices, Gabor features, histogram-oriented gradient features, and so on. You would just use all of them, put them into a ConvNet, and then you do your classification. And of course, this works well, right? It's not too interesting, but it's a first step to use ConvNets on SAR images. Interestingly, right, random forest didn't behave that badly as well, right? So random forest was like nearly 90%. This proposed ConvNet was 93% on this data. Then the next step was to say, okay, come on, guys, we are SAR people, right? So let's not just use standard features and ConvNets that were developed for optical data, right? Let's come up with our own things that are specific to SAR. And in this example, they tried to do that. So they had this complex valued SAR image, where they used an intensity image for one ConvNet, and they used a certain feature extraction spectrograms that can only be done for SAR images, for complex valued SAR images. And they used this in a second network. Then they fused those two things, put it into a third network, and that was then doing the classification. So those spectrograms, what they're basically doing, I can't go really into detail here, but it's deeply into the SAR focusing. But what you can imagine is that you have this long aperture, the synthetic aperture, right? It's a movement of your sensor, and you can cut this into parts and use each part only to do a certain, to do the focusing only for this part. And then you take the next part and only do it in this part. So this is called sub-apertures, and you can do something very similar to that also in range direction. And in this way, you obtain basically either slightly different look angles of your object or slightly different frequencies that have been used for the processing. And some objects that can look very similar in intensity images can behave very, very differently with respect to those parameters. So they computed those four-dimensional spectrograms. Right here, you see different visualizations of that, and used them as input to a ConvNet. So they have those two streams, right? The first stream was working on an intensity image. Here they also used pre-training. So they had intensity images and a network that was doing just a classification in different things. Then they used part of this network as input, or well, this part also as part of their stream network here, attached a couple of layers, and then that was the representation they learned from this stream. Then they had the second stream that was taking this spectrograms into account. Also, this one was pre-trained by an autoencoder. So Cora, coming back to your questions before, right? So yes, autoencoders are used also for SAR. So here we have a stacked autoencoder that is trying to reconstruct the input spectrogram to itself by a learned representation. And then this encoder is again used in this second stream of the complete neural network architecture. Then a couple of layers again to learn some more features. Then those features are concatenated with each other. A third small network that is then doing the classification. And this works quite well. In particular, it works better than only having a ConvNet that is only working on the intensity itself, so only on the SAR image. It works as good as the standard ConvNet for natural surfaces, but it works much better on man-made objects. And I think the reason is that the spectrograms over natural surfaces, very often you don't have too much information there. Sometimes yes, but very often not. But over man-made objects, you have this a lot. So there should be a lot of information in the second stream, and I would expect that this is why it works better. All right, but both of those networks, they still used real valued convolutional networks, right? Standard convolutional networks that were developed and designed for optical data. So the next step was obviously to use something that is directly working on our complex valued data without any kind of real valued feature extraction. And that's what they tried in this work. Here, the idea was that, well, we have our input maps that are, or input images that are real valued and imaginary valued. And we have our kernels still real valued. And now they applied those real valued kernels individually to the real valued part of the signal and to the imaginary part, right? But the same kernels. And then they just attach this again to a complex number, right? So you decompose and compose this complex valued signal and apply the kernels individually to that. It's the first step, but it also works quite well. So here you see how this network was used in crop classification over multi-temporal sentinel images. And then the obvious next step was that we are also using complex valued kernels. So this was one of the first works that were doing that for ConvNets. There are earlier works that were doing that for standard MLPs. And here the challenge is really that once you have complex valued signals and complex valued kernels, your whole network becomes complex valued. So this also means you need to have complex valued activation functions, loss functions, and so on. So this is what you see a little bit here on the right-hand side, right? So this is a complex valued activation function, just the standard logistic function. This is a complex convolution, right, that is going on, where of course you need to make complex value multiplications, right? And the main challenge, however, is that you need to do the whole backpropagation in the complex domain as well. And this is getting quite ugly. So here you see a small part of, for the backprop, you need the derivative of your error with respect to the weights. The weights are now complex valued, right? So you need to compute the derivative of the error with respect to the real part of the weight and the imaginary part of the weight. And then, it's just becoming very, very complicated to do this, but it's possible. So nowadays, we also have complex valued neural networks. They've evaluated that on, unfortunately, only a small SAR image, right, with all the drawbacks I had mentioned before, but at least here they have shown that you get a performance improvement by quite a bit compared to a real valued neural network. All right. And the last part, I want to cover something that was also asked by the participants before. So I really appreciate your input there. The question was, can we use optical data to somehow help the neural network understand SAR data, right? A couple of directions you already have seen in the last examples. And here I want to show another example, which I personally like quite a bit. And the motivation was a little bit that there's a lot of academic research for convolutional neural networks. But if you look into how SAR data is processed and analyzed in practice, there's not much confidence going on, right? They are not operational yet. There, it's other methods. And you also see this if you look at challenges. So very often, and this is just one example where SAR data was analyzed for a certain task, the data fusion contest from 2017, all the leading places were ensembles, right? No neural networks. Some of them included neural networks, but only like one of many components, right? And the reason was not that they didn't try it. So this shows the accuracy of the submitted solutions over time, right? So over time, accuracy got better. And the deep neural networks was the first thing they tried, but it just didn't work, right? And then they went to boosting, and at the end, ensemble techniques, and then the winning approaches were all ensemble techniques, basically. And one of the reasons is that we don't have enough data for SAR images that are labeled. And we need, for deep learning, we need a lot of labeled data. So if you have this kind of task that you have a SAR image, in this case Sentinel-1, and you want to produce a semantic map, right? You only have a few labeled samples. So you can do this. You will get a semantic map, but it won't be very, very good if you only have few hand-labeled samples. If you have a lot of labels, then it will work very, very well. But usually we don't have that because labeling SAR data is really, really hard. You have seen all the efforts the other papers went through in order to produce that. And you can see this also here. So blue and violet are two different convolutional neural networks trained on a different amount of training data. Right? So here it's all the training data we had, and this is only 1/16th of the training data. The green one is a random forest, a special random forest that is also doing feature learning, but just a shallow learning. And you can see that this shallow learning is actually outperforming the deep learning by quite a bit if you only have a few samples. If you have more samples, everything is getting better. At some point, it's competitive, right? And only when you have really a lot of data, deep learning is starting to outperform the shallow learning. So now the idea was that we try to do a transcoding. So we have a radar image and we have an optical image, and we try to use a neural network to take the radar image and produce something that looks like an optical image. Right? Very similar to the approaches you have seen before. Right? So here you see some examples. So this would be the input radar image, and this would be the synthesized optical image. So the idea here is that this is not a trivial task, right? When the network is able to solve this, it needs to understand what kind of texture does a forest have, and how is it different from the texture that a city has. We never explicitly tell the network what is a city or what is a forest, but in order to solve this transcoding task, it needs to be able to distinguish between different land cover classes to synthesize the correct optical texture. So in this way, the network will learn very meaningful features that then can be used. So here you see a couple of more examples. This would be the input radar tiles, Sentinel-1. This would be the real optical tiles from Sentinel-2, right? So you have a cloud here, for example, and that would be the synthesized fake Sentinel-2 optical tiles, right? Produced from the radar. As you can see, it's not perfect, right? There are differences in colors, difference in shapes, but more or less the network got it right. In particular, of course, there's no cloud, because in radar images there are no clouds. So now, actually, we do not care about this transcoding result. It's just a byproduct. We basically throw it away in this approach. Instead, we are using the features that this network has learned as input to a classifier that is then producing our semantic map. So this is the architecture that we use, right? The radar tile goes into the generator of the GAN. We have here decoding, the encoding again. This is producing the optical tile, and this optical tile is input to the discriminator, which needs to decide whether this is a real optical image or a synthesized one. We could this also with a regression network, right? Without the discriminator here, just put a regression loss over here. That also works, and the images look like this, right? So those are synthesized images from a radar tile, but just with a regression network. So in general, you know, like it looks okay-ish, but it looks quite blurry, right? Because regression is like a mean squared error, right? So it's just average. But again, here you have like different possible solutions to certain input, and what the regression network will do is just average, and that's why it's getting so blurred. Now, if you do the same thing with again, it looks much better, right? So here we have the texture that is correct, much more details, and so on. Many of those details will be hallucinated, right? Because the corresponding information is not present in the SAR, so the GAN will just hallucinate that. So interpreting those optical images, there you have to, take them with a certain sort of grain. But in this work, we don't do that. Instead, the features that have been learned by this generator, we now use in a classifier, right? And then we just retrain this classifier. We have two Sentinel images for that, two pairs of Sentinel images actually over area in Poland. We hand labeled a couple of millions of pixels in both of them. We use one image for training and the other one for testing, and for training different amounts of data. And here you see again the plot from before, right, with the two convolutional networks that have been trained from scratch on different amounts of training data. The random forest, right, the shallow learner that was outperforming the deep neural network for a small amount of data. And now we have two versions of this proposed technique with the pre-training for the transcoding. And you can see on the one hand, it's very robust with the number of training samples for the fully supervised training, right, the fine-tuning of the classifier. Because a big part of the network, if you go back to the architecture, a big part of the network is already trained on the transcoding task. And we only need a few samples to fix the parameters of the classifier. And it's outperforming the shallow learner by a big margin, even with a lot of samples. And it's also outperforming the two neural networks that had been trained from scratch. Right? So this is an example I like a lot, how you can use other types of data to pre-train parts of your network, and then still apply this to SAR only and have a really, really nice performance. So here you see a couple of example images. That's the input SAR. The optical is just for reference. It was not used. So this is the reference data. Those are the two networks that have been trained from scratch, either only on a small part of the training data or all the training data. Right? It's making big errors, as you can see. And here you can see the self-supervised network that was trained on the transcoding with a small amount of labels or all the available labels. You can see the solutions is quite stable and very much consistent with the reference data. All right, other questions?
There are some questions on YouTube.
Mm-hmm.
I can read them.
Thank you.
First one is, in building 8 estimation, the only auxiliary data was the GIS data, right?
Mm-hmm. Yeah. Let me briefly go back to this just to make sure that we talk about the right thing. So I think you mean this one here, right? So yes, the only input is the SAR image right? And this part of the footprints from the GIS data. This was part, those are the two inputs to this neural network, right? In order to get this predicted buildings. But in this way, you get the building footprint, right? I mean, that is what you have already from the input, from the GIS. And on the other hand, you also get the layover part. And now you can, the layover depends on the geometry of the sensor, but that one is known, right? You do know where the sensor was, and on the height of the building. Then you can relate the layover to the height, actually. In the paper, they have a very simple equation how to do that. So you can use a detected building part, so that was detected here, in order to estimate the height. And that works quite nicely, surprisingly well. But yeah, there's no second radar image, there's no LiDAR, or there's no INSAR or something like this. It's just this one radar image and the GIS information is input.
The second one, is the solar parameter included in the calculation? Because the shadow of the objects changed according to the angle of the sun. I think it's the
can
solar,
you repeat?
Is the solar parameter included in the calculation? I think it means this calculation of SAR, maybe.
The solar
solar parameter included in the calculation.
Okay, I don't completely understand it.
Related with the shadow.
So I don't follow the question completely, but I can try to answer nevertheless. If it's not the answer you were looking for, then just reformulate maybe. So in the formation of the SAR image, no, right? I mean, in the formation of the SAR image, of course, you need to, the position and the look angle of the sensor very, very accurately, like crazily accurately, in order to focus your SAR image. But this then will give you the shadow, right? Now, the shadow, by analyzing the SAR images, is implicitly taken into account, I would say. So if you talk about object detection, let's go back to where did we have that? That was too far ago. If you take about something like this, for example, right? So here you would use a patch, right, around a certain spatial neighborhood. And of course, this spatial neighborhood, it contains the object signature, it contains layover area, maybe if the object is high enough, and it contains also shadow area. So the Confident has access to all of that. And of course, it's processing all of this together. Just like how it's always with deep neural networks, you don't understand what it's doing there exactly, right? But implicitly, the shadow is used. The problem with the shadow is that it varies quite a lot for like different look angles, right? So different incidence angles. So this means you have a variation in the shadow signal that is depending on the sensor and not depending on the object. And if you don't normalize for that, then this variation, I think, is too strong regarding with the signature of the object itself. So very often, my assumption would be that the shadow is very often a little bit mistreated by the ConfNet if you don't normalize it. But of course, you can take this into account. You do know the incidence angle, so you can try to detect the shadow region, normalize for it, and then help the neural network a little bit. There are also approaches that try to estimate shadow, object part, layover, and so on to detect that in the image, and then have, like a machine learning approach acting independently on those, and then fusing the results and then make the final classification. So I would say it's always taken into account implicitly, because you always look at a spatial neighborhood around your object. And there are some approaches that try to take this into account explicitly as well.
Okay, there's also another question in Q&A section. In the complex CNN, is the loss function still a complex number?
Sometimes yes, depends a little bit. So you do have loss functions that are indeed complex valued, in the sense they take two complex numbers as input and produce a complex numbers output as well. In this case, you would take like the absolute value or something like this in order to have scalar, in order then to derive the derivative. Because I mean, you still don't want to have two outputs, at least not for the object detection case. There are other loss functions that are taking two complex numbers as input and produce a real number directly. So both cases, but if you have a complex valued loss function where the output is also complex valued, you would project that into the real domain in order to have an easier derivative.
I think there's no any other question.
Okay.
For now.
Yeah, perfect. I have to say I'm very good in time. So we have covered all of this. I have 15 minutes left, correct?
Yes, we have 15 minutes.
Perfect. So now we have heard a lot about how SAR works, how can we use deep learning in order to increase the quality of SAR images or SAR products. And you have seen examples, how can we use deep learning with SAR imagery for solving different generic tasks. In the last 10 to 15 minutes, I just want to go through some interesting applications. There are, of course, many, many more. So those are just some examples, but yeah, some, I hope, interesting examples. So the first one is crop classification. So in this paper here, they use Sentinel data over Denmark. And I really like this because they used a really big data set. So they have like 500,000 hectares for training. Those are the red areas here. And they have half of that, more than half of that, 250,000 hectares for testing, that are the blue areas. And in each of those areas, they have a temporal Sentinel-1 stack. So a lot of images that were acquired at different timestamps. And they want to use this for crop classification. So additionally to this input data, what they also have is information about the crop types that were planted during this time, right? For quite some different classes. And the data was acquired during the main growth season, right? So it would start at a very early stage where the plants are not really there or just a little bit there, then covering the time where the plant is fully grown, and then a little bit going after the harvest. They use the standard ConfNet, right? It's just a standard unit architecture with two tweaks to it. So the first tweak is, well, they use multi-temporal data, right? Then they have this encoding layer, the decoding layer, and some skip connections. And then the first tweak is that here they have an LSTM, a long short-term memory cell, right? So this part here is analyzing the temporal features. And the second tweak is that they are using metadata, mostly the time of the recording and the different incidence angle of the satellite. So this is what they use, and at the end they want to know, in this time series, what kind of crop type do we have in the different pixels. And that worked very well. We have to keep in mind the data set is imbalanced. So there are like 3 classes that are covering like 60% of the data. You have to take this into account when you interpret the accuracy, but in general, the accuracy is very well, right? So here you see the confusion matrix. This is what it actually is, and this is what it was predicted. And here on the main diagonal, the more darker green, the more accurate it is. And you can see most of the samples have been corrected correctly. There are a couple of problems. The first one is this one here. How was it called? That is green grain spring barley. And it's mainly confused with spring barley. So with this one here. And the reason is that it's the same plant, just planted at different times, right? So the only difference is really like a temporal shift in the signature that you observe. So this explains this confusion. The other confusion is permanent grass down here that was confused with the background class. And the reason is that, well, the background class was basically everything that is not an agricultural field. And well, a lot of things that are not in agricultural field is grassland, right? Or urban areas and so on as well, or water areas, but also a lot of grassland. So this is why we have a big confusion here. But in general, the accuracy was working rather well for crop type classification on multi-temporal data. What they also try to look into is how does it change over time. So here would be the input image, one of the input images. This is a reference data. This is the prediction, and this is the error map, right? So if it's black, it's correct. If it's red, it's an error. And you can see that it's getting better over time. And there are two reasons for that. Two reasons, at least, they stated in the paper. The first thing is early in the year, the plants are very young. And at an early growth stage, the plants tend to look very, very similar to each other. I mean, in the extreme case, they're not out yet, right? They're not grown at all, and you just have bare soil. Of course, you can't distinguish that then at all, right? Then they come out a little bit, they look very similar to each other, in particular, taking the resolution of the Sentinel-1 sensor into account. And then they need to grow to some point in order to really be able to distinguish them. And then the other thing is that if you have longer time series, you have more temporal information available in order to make better predictions. And you can also see how this develops for the individual classes, right? So those are the accuracy curves. It's an intersection over union. They have taken here over time for the different classes. And you can see the accuracy improves for all of them over time, for some more than for others. But yeah, it improves and then it saturates to some extent. So I found this very interesting and a very nice study because the data set is big. The data set is well distributed. You use spatially disjoint areas for training and testing. You use multi-temporal data because this is what Sentinel can really provide. It's free data. And you can solve a very important task, which is crop classification. A little bit connected to that is forest classification. So in this work here, they used INSAR data by the Tandem X sensor, right? So those two TerraSAR X sensors that are flying in constellation. You can have different measurements for that. So you can have the backscatter amplitude. You can have the local incidence that is also depending on the topography. You can have the complete decorrelation, right? So the coherence of the interferogram, or you can try to estimate only the volume part of this decorrelation. And then you can use this as an input to a neural network. Here they use, again, a standard UNet, right? Encoder, decoder with skip connections. So you can have here different inputs, any of those combinations, and then you estimate whether it's high vegetation or not, forest or not. And here you see some results, the optical image just as a reference. This would be the reference image, right, the ground truth. And now here the results of the conflict for different input combinations. And the best one is if you use all three of them, right? So there's a volume decorrelation, the backscattering, and the incident angle, and then you have very nice results. One task that is a little bit connected to that is wildfire estimation. Right now, a very timely topic, a very important topic. Of course, also here, so this is a quite elaborate method. I don't have the time to go through all the details, but the gist of it is you have a time series of SAR images. You select one image before the event, before the time, before the wildfire, and one after. You produce an image stack of those together with other products, for example, an elevation model. You put this into your ConfNet, right? In this paper, they had also a semi-automatic procedure to produce the training data, the labels for that, which with the ConfNet was trained. And then the output of the ConfNet is producing a burn map. So a segmentation map of areas that have been burned by the fire. And then you can do this for different timestamps. So here would be different visualizations of the input images. This would be the prediction of the neural network. Then you just threshold this. You do different types of merging. The final output would be like this over different time steps. So you can see here how the forest fire is starting, and then how it is distributing, and how the burned area is increasing. Another application are volcanoes and automatic monitoring of volcanoes. Here they used CNN to detect deformations of volcanoes. They started with interferograms. They did an edge detection of the interferograms, cut out certain regions based on the detected edges. containing negative samples and positive samples of volcanoes. This is how they trained the neural network on, with detecting whether there is a ground deformation or not. And then they could use this trained neural network on new data, where they basically did the same thing. They have this interferogram, they do an edge detection, cut out the corresponding potential candidates, and then have a confident deciding whether those candidates show an actual deformation or not. And then a couple of post-processing steps that then show where the deformation is going on. They collected a really big data set of interferograms from volcanoes from all over the Earth. So again, a very large data set. Here you see some examples. If we zoom in, just in order to illustrate why this is a hard problem. So those would be positive examples where we actually have ground deformations. Those would be negative examples where there's no deformation. What you're seeing here is actually changes due to an atmospheric signal. So this is what you want to detect. This is what you want to sort out. And it's also working very well. So it puts this into a ConvNet in order to detect the deformation. This is another example for volcano monitoring. What you would see here is a false color composite of two SAR images, sentinel images. Here you see the lava flow, basically. This is an optical image with a lot of clouds and dust, of course. So the first SAR image was taken here, then here there was an eruption, right? And then the second SAR image was much later. They trained a CNN on synthetic data, so synthetic interferograms, estimating the coherence as well as the phase gradients, right? The phase gradients are depicting the deformation. And then they applied the CNN on real interferograms taken from Sentinel-1 images. So they had a script that was automatically downloading Sentinel-1 images from volcanoes, applying the CNN to the interferogram that would estimate the coherence as well as the phase gradients. The phase gradients would give you the information about the deformation. And if the deformation is going over a certain threshold, then you would issue a warning. And that also worked very well. So here you see this deformation score they have estimated over a time series of interferograms, right? So all those peaks mean that there's a detected deformation going on. This one here is from the SPIR sensor. So it basically corresponds to hot pixels in the scene. And you can see that those detected interferomeric deformations correspond very well to those lava flows, right, to the detected heat pixels, and also very well to the actual volcanic eruption phases that had been, well, observed on the ground by the ground stations. And the last example is slum detection. This is a very nice example for transfer learning, because what the people did in this paper was they trained actually a ConvNet on QuickBurg imagery, so on optical images, and then they were transferring it to different sensors, including Sentinel-2, so also optical or multispectral, but also TerraSAX, so a SAR image. Standard ConvNet, again, you put into your image a couple of convolutional pooling, then a couple of upsampling layers in order to predict your final label. And again, it worked rather well. So although it was trained on QuickBurg imagery, they were able to transfer that successfully to TerraSAX, at least to some extent. Transferring it to other optical images worked better, right? So the best approach was with Sentinel-2. But even for SAR, so going from optical imagery to SAR, still worked to some extent. You have a decrease in performance, but not as much as you would expect. All right. So in the last 2 minutes, I just want to quickly go through some data set and benchmarks. This data set we already talked about. This is a optical data set that is used, where they aligned the tomographic and photogrammetric point clouds. It's used for training ConvNets for co-registration. This is another data set where you also have aligned patches of Sentinel-1 and Sentinel-2 images for the same goal. For image classification, there is a SO2 set data set for local climate zones. So they have a lot of different climate zones defined and corresponding Sentinel-1 and Sentinel-2 image patches also aligned to that, to those semantic classes. Another example is OpenSAR Urban, where again you have Sentinel-1 patches distributed over cities in China with different urban classes. For object detection, we have OpenSARship 2.0 that has different ship informations taken from Sentinel images. There's also AirSAR ships that is coming from a Chinese satellite. For semantic segmentations, we have SEN1-2MS, where you have Sentinel-1 images, Sentinel-2 images, and then semantic information from the Korean land cover map at a very coarse resolution. And then there's the SpaceNet 6 data set that is only acquired over Rotterdam. It has polarimetric SAR data, also optical data, and thousands of building footprints. And with this, I end my lecture right in time. So thanks a lot for joining. Thanks for being interactive and asking questions. If anything's still unclear, I'm not sure how much time you'll still have to answer a couple of questions. Feel free to reach out to me in any way you see fit. Happy to talk to you, to discuss, to brainstorm ideas, or to collaborate. All right,
Thank you very much.
Exactly 12 now, so I'm not sure whether I'm still allowed to take some questions or whether we go into the lunch break.
I think there's one question in the YouTube.
Hmm?
In YouTube, there's one question. Is there any code repository to examine these topics?
Oh, yeah, very good question. Yes, there is. So in remote sensing, people don't share their code, or usually they don't share their code, which is really bad. In computer vision, it's very common that you share your code. It's partially even mandatory. So luckily, people now also start to do this in remote sensing. There is GitHub where you can search. So a lot of the approaches that I've presented today, you can find actually on GitHub repositories, which is really nice. So you need to search there, read the paper, check the department's web pages. Then, of course, there is a remote sensing code library that could be used a little bit more. I'm not sure whether there's a lot of deep learning on there, but people start also using this. And then there is IEEE Code Ocean, which is for not just remote sensing, but in general, where people also go with the code. I think the most heavy used resource is GitHub. And well, you would need to search for yourself there or read the papers where the authors put their code on GitHub.
Okay. Is there any question from organizing committee?
Well, I would like to thank on behalf of all of us to Ronny. This was a very well prepared and very informative lecture. I think not for SAR people, but for anyone working on remote sensing. So thanks a lot.
My pleasure.
I personally don't have any question. I think it was very clear. I'm interested in some topics, but maybe we can keep in touch later, personally by email on that.
Definitely.
Thank you very much.
Then,
it was a very nice presentation. Even though I'm not a SAR person, I learned a lot from your presentation. Thank you very much.
I'm glad to hear it. Yeah, thanks for having me. I also enjoyed it.
Yes, we would like to thank you for this very nice presentation and for being us in this summer school. I hope it will be very beneficial to the participants. So we can close this session here. The next session will start at 2 o'clock in local time, Turkey time.
Thank you to all the participants.
Thank you, everyone.
You enjoy the rest of the summer school. Bye, everybody.
Thank you.
Take care. Bye-bye.